Hello everyone. In today's class, we are going to discuss the class of problems which is called as knapsack problems. Over the last couple of sessions, we have discussed several problems that we can solve using the DP paradigm of solving problems. And today, we are going to discuss a specific class of problems that is called as knapsack problems. Okay. Let's begin today's class. How many of you know what knapsack problems are? So let me first of all start the class by defining what are knapsack problems. And once you know the definition, you would be able to appreciate that yes, this is a specific kind of very niche kind of problem set that we hope to solve using the concept of dynamic programming. Okay. So first of all, knapsack problems are basically optimization problems. What is meant by optimization problems? That is, you're trying to optimize a particular construct within some constraint. Okay, so you're trying to optimize something within some given constraint. There is a constraint that is given to you, and you're trying to optimize some other value based on that constraint. Okay, cool. In these knapsack problems, these problems are in general exponential time. Okay, in general, you will require exponential time to solve these problems. I hope you guys understand what is exponential time, right? So something which is not polynomial, right? So you are having a value raised to some power. Okay, so this is exponential time in terms of the input parameters that you get. But these problems become very, very interesting because there is some other constraint in the problem which is other than the number of the problem size, which makes these problems solvable in polynomial time. Please understand this very, very carefully. In the set of knapsack problems, there is some constraint. We will see what this constraint is in different knapsack problems. There is some constraint which is other than the size of the problem, which makes the problem solvable in polynomial time. Now we are going to see what kind of a constraint we are talking about here. Okay, cool. So keep these things in mind, and do not worry if you did not get it completely at this point in time, because now I'm going to define the problem for you, and then looking at that problem, we are going to fall back to these points that I just wrote, this definition, and see if that problem actually falls into this template or not. Okay, cool. So let me define the problem for you. Here is the problem. Let's assume, unfortunately, you are a robber. Okay, that's a very unfortunate thing to assume, but let's assume you are a robber. Okay, good. Now you go to a supermarket. That supermarket has n products. Okay, there are n items in that supermarket. Okay, cool. Now every item in a supermarket, you would realize, has some value associated to it. Does that make sense? What is the value? Let's assume the MRP. Okay, so every item has some value. Let's assume the first item costs rupees 60. The other item has the value of rupees 100. The third one has, let's say, 120. Fourth one is 50. Let's assume the sixth one is 70, and the last one is, let's say, 20. These are the values of those items. Okay, every item has a value. Not only that, but you would also realize that every item also has some weight. Does that make sense, folks? Every item will also have some weight associated with it. So let's call it the weight. Okay, so let's say the first item was weighted 10 grams, let's assume. The second one was 20, third one was 30, fourth one was, let's say, 5, sixth one was, let's say, 52, seventh one was, let's say, 100. Okay, so there are different weights given to different items. Okay, so every item has a value associated, every item has a weight associated. Cool. Now the problem that you're trying to solve, just because you are a robber, the problem that you're trying to solve is basically that you want to rob some items of this supermarket, but you brought with yourself a bag. And let's assume you are somebody who wants to save the earth and does not believe in, let's say, using plastic bags. You got a good big bag made out of clothes from your house, right? So even though you are a robber, but you are a robber with your own set of beliefs, right? And you do not want to hurt the environment, and you have a bag, cloth bag that you brought with yourself. Okay, cool. Now, if you have a cloth bag that you brought with yourself, let's assume that bag had a weight, a maximum weight that it can take. Okay, so that bag has an inherent maximum weight that it can hold at any given point in time. If you add any more item beyond this maximum weight, your bag is going to break and you are going to lose all the items. Does that make sense? So let's assume this is the problem. You go to a market, there are n items, you want to steal some of the items. Every item has a weight, and there is a bag that you got to steal those items, and that bag has an inherent maximum weight that you can put. Okay, now I would just mathematically define this problem for you. I have given it intuitively. Let me just define the mathematical problem that we are trying to solve here. Okay, the mathematical problem that we are trying to solve here is that, of course, you would want to maximize your loot. Does that make sense? So you would want to maximize your loot. Okay, so let's assume out of these items there are n items. Okay, let's assume I stole some of those items. Okay, so you would want to maximize your loot. What does it mean? You want to maximize the value of your loot, right? Maximize the value of your loot. But there is a constraint. The constraint is that the items that you looted, the sum of their weights should be less than equal to the maximum weight that your bag can have. I hope it makes sense, right? This is the optimization problem. The constraint that you have basically is that is the sum of values, sum of weights of the items you stole should be less than the maximum weight of the bag. I hope this is crystal clear to everybody. Let me just write it once again. So you want to maximize the summation of values of the items you loot. Okay, I looted items. So the sum over the values of the looted items. You want to maximize this such that the summation of weights of the looted items is less than equal to WP. I hope now the problem should be clear to everybody. The problem should be clear to everybody in the class. This is the kind of problem that we are trying to solve. Now think about this problem, and the first thing that you should ask yourself is, can I solve this problem greedily? Okay, this is the first thing that you should ask yourself. Can this problem be solved greedily? And I would want you guys to take a minute and see, can you solve this problem greedily? And let me just state one thing here, which may not be very clear otherwise. The one thing that I wanted to state here is that this problem is a real life, let's say a 0-1 knapsack problem. What does that mean? That means that you can either pick an item completely or you can not pick an item at all. Okay, so you can either pick an item one time or 0 time. That is, either you can say I will pick the complete item one time or I will not pick that item at all. I hope this makes sense. Now, can you guys think about whether a greedy solution will work here? Okay, think about it for a minute. Right. So the answer here, folks, is that let's try to evaluate whether a greedy solution will work for us or not. Okay, greedy solution. I would have told this to you guys in the previous classes that I have taken online. You would have seen that greedy solutions work for problems. So what is a greedy solution? Greedy solution says that you are taking a decision which seems best to you at this point in time. What does that mean? That let's assume you have a sequence of numbers, or let's assume you have a big problem that you have. You are just taking a decision at this point without looking at what is there in the problem going forward. Just looking at a particular point, taking a decision that what is the best solution. That solution would look to you the best option at that point in time, but will also guarantee that if you keep on taking that best solution at that point in time, the overall solution that you get is also going to be maximized, also going to be optimized. What does that mean? It simply means that you are building a solution, taking local optimizations, which is going to yield to you the global optimization. Okay, cool. So let's try to look at this problem here. The point is that you would want to maximize your global value of the loot that you had. Okay, now my question is there any way in which you can just look at this item and figure out whether this item should be stolen or not? The answer to that would be that no, you cannot do that, because no matter what parameter you apply, let's say you apply a parameter which tells you that amount of value that you can get per unit weight. So what does that mean? So that would mean that the first item would give you a value of 6 per unit weight. If you guys are able to understand that, you get the value 60 with 10 grams of weight. So you get 6 value per unit of weight. Here you get 5 value per unit of weight because you have 100 value with 20 weight, 5 value per weight. Here you have 4 value per weight. Here you have 10 value per weight. Here you have 70 by 52, which is going to be 1 point, let's say 3, 1.3 1.4 something. Okay, and then you can have 20 value with having a weight of 100. Okay, so that basically gives you the value of 0.2. Now, can you take a decision here just by looking at, let's say, these things and saying it just because this value has the greatest value per unit weight, I would want to go with that item? The answer to that is no. You cannot make that decision no matter what kind of a ordering you do. The reason being that there is another bag. The moment you take some item, you remove some possible weight from the bag, right? So you have assume that you have filled that bag with some weight. Okay, and now going forward, there may be a scenario that you are left with some weight in the bag that you can never fill. On the other hand, if you chose not to include the value which was giving you the best option at that point in time, maybe you can select some combination of items going forward which would maybe completely utilize the value weight of the bag and give you the maximum value. Does that make sense to you guys? So these kind of problems, when the landscape is changing with every decision that you take, and with every decision that you take, the further options that you have in that problem change drastically, you would not be able to come up with a greedy solution. I hope it makes sense, right? Cool. So first of all, we just discussed that a greedy solution will not work in this case. Okay. One thing that you guys would, again, I'm repeating it again based on my last sessions. I would have said that if you see a problem where a greedy solution won't work, then the other option that you have is trying to explore every possibility. What does a greedy solution do? A greedy solution sort of gives you one option or a couple of or a constant number of options at every step, and you say that okay, I'm only going to take these options and these are the greedy best option, and I will not be worried about what happens if this does not work out. This will always work out. But whenever the greedy solution does not work, the other option that you have, so if this does not work, the other option that you have is to explore all possibilities. To explore all possibilities. And whenever you see a problem which is forcing you to explore all possibilities, what does that mean? So in this problem, just because I cannot take a greedy decision, I will have to explore every possible option, whether to pick 60 or not to pick the first item, whether to pick the second item or not to pick the second item, whether to pick the third item and not to pick the third item. And these are not independent events. These are consecutive events. So if you pick the first item, then do you want to pick the second item or do you not want to pick the second item? Or let's say if you pick the first item, did not pick the second item, do you want to pick the third item or do you not want to pick the third item? So these are consecutive decisions that you are taking. And these kinds of decisions, if you want to explore every such possibility in any decision, then one possible way that you should think about is the class of DP. Okay, is the paradigm of DP, dynamic programming. I'm not saying that every problem that where you want to do explore all possibilities, DP would be working, but this is one possible thing. If you are, let's say, giving an interview and you see a problem which really does not work, you are forced to explore all the possibilities there, then it should come to your mind, can I model this problem as a DP solution? You will not be able to do it for every problem, but for some of them, you will be able to do it. Okay, I hope I have made myself clear. Now, for DP, I told you that there are two very important parameters that you need to see if a problem has, only then it will be able to broken down into a DP. These are, do you have optimal substructure? That is, can you use the answer to smaller problems to solve the answer to a bigger problem? And the second thing was, do you see overlapping subproblems? So can you actually say that once you end up doing this, so this is something which takes you the recursion way. So you can build a recursive solution there, because if you just can use the answers to smaller problems, you can build a bigger answer. You can use recursion out there, right? This takes you recursion way. But the moment you see that in all the states that you get in the recursion, if there are repeated states that you are getting, it makes the problem dynamic programming problem. Okay, you can afford to not compute those repeated states and solve the problem in a very, very fast manner, right? Now, I am pretty sure that for some of you, this may seem a bit too fast, but I would request you guys to look at the first two videos that we did. and I explain these things in great details. And I'm pretty sure that once you look at those videos, you'll be able to understand what we are talking about here. Okay, cool. So we realized that this problem, first of all, cannot be solved greedily. Now, can I look and see whether a DP solution will work here? Okay, cool. So you guys can, let's look at a smaller problem here. So let's assume if you had the answer to problems from here to here, that is, let's assume there were only 3 items and you know what is the best loot that you can get, or what are the different loots that you can get at different weights. Can you utilize that answer to figure out, take a decision for the fourth one, right? So I will just try to explain it using the recursion tree. Just a minute. Right. So let me just try to define this problem using a recursion tree. Okay, good. So what is the point that you have here? So let's assume you have different options to take. At the very first step, let's say you have an option of either picking. So let's say you are at the first element, I is equal to 1, and the weight in the bag is, let's assume, the weight maximum at the moment, because you have not included any item. The weight of this bag is that is available, so let me call it weight available, is the maximum weight of the bag, and you have to take a decision for the first item, and the value that you have aggregated till now is 0. Does that make sense? Before you have done any decision. So let me define the arrays once again, and let me maybe have a smaller array this time around. So this is the value, this is the weight array. These are the 2 arrays that we had, value and the weight array. The values were 60, 100, 120, and 50, and the weights were 10, 20, 30, and 5. Right. So these are the values and the corresponding weights. And let's assume the weight of the maximum weight that you can put in the bag is, let's assume, 50. Right. Now at the first position, let's call it 1, 2, 3, 4. At the first position, before you go to the first position, your value aggregated is 0 because you have not selected anything, and the available weight in the bag is weight maximum, and you have to take a decision for I is equal to 1th item. Now you folks tell me, what all options do you have at the first item? There are, the element of choice that you have is that you have 2 options. Either you can say that I am going to select the first item, or you can say that I am going to not select the first item. Does it make sense to everybody? If you select the first item, can you define these 3 parameters for this new state for me? I am pretty sure that you can. You have taken a decision for the first item. What is the next item that you will have to take a decision for? For sure, you will have to take a decision for I is equal to 2. You have chosen to include the first item. Can you tell me what is the value aggregated till this point in time? The value aggregated till this point in time would be the value of this item. Does that make sense? Because the value previously was 0, I have chosen to include the first item. The value aggregated till this point in time would be the 60. Okay, so this is done. You have to take a decision for I is equal to 2 now, and the weight available that is there in the bag. So you guys tell me. Initially, the weight available was 50, right? Now you have included the first item. The weight of that item was 10. So can you tell me the weight available now? The weight available would be 40. 50 minus 10 is 40. So this is how you take this. This becomes one state. If you chose not to include the first element, can you tell me what to do now? So you have taken a decision for the first element. Now what is the element that you need to take a decision for now? The second element, right? So you have taken a decision for the first element. Now you need to take a decision for the second element. Value aggregated before was 0. You chose not to include the first element. The value aggregated till this point in time will also be 0, right? And then the weight maximum, the weight available before was 50. You did not select the first item. The weight available will still remain 50. I hope it makes sense that this one state now boils down to these 2 states, right? Now let's look at this state. You have to take a decision for the second item. So again, you have 2 options. Everybody in the class, understand please. Again, you have 2 options. The option 1 that you have is you will want to select the second item. The second option that you will have is that you will not want to select the second item. If you want to select the second item, you would agree with me that now you need to take it for I is equal to 3. The value aggregated till this point in time would be equal to 60 was till this point in time. You are selecting the second element, which will make it 160, right? So you make it 160 is the value that you have chosen to steal till this point in time. And let me also define the weight available. The weight available would be 40 was before this. You just included a value, a weight item which has the weight 20. Now your weight becomes 20. The available weight becomes 20. I hope you guys are able to understand how this recursion tree can be built. Whenever you see a problem which has at least the optimal substructure. That is, here what we are doing to compute the answer of this, we are actually using previous states. Does that make sense, folks? Does that make sense? So basically, you will understand that whenever you have optimal substructure in your problem, the way to go forward would be to draw a recursive tree. Once you draw a recursive tree, I will tell you how to take the problem forward. I'm sure everybody is with me that you define this problem. So the moment you understand there is optimal substructure, you draw this recursion tree. Once you draw this recursion tree, you see how the states are being modeled, and then you can move ahead and see if DP can be applied there or not. Cool. Now, for DP to be applied, I told you one problem is optimal substructure that we already see while building this recursive tree. The second problem that we have is overlapping subproblems. If you have overlapping subproblems, then you can make an argument saying that this problem can be solved much better in a much more optimal manner if I choose to actually utilize the if you see overlapping subproblems, that is, there are subproblems that you already computed and you need not compute now. Looking at this problem, do you see that there are so many overlapping subproblems? The answer to that can be figured out by looking at the number of unique states that you have in this recursion tree. So try to find out number of unique states in this recursion tree. Try to find that out, folks. So you tell me, every state here is defined by three parameters here: value aggregated, I, and W max. Okay, there are three parameters: value aggregated, I, W max. I can say that I can model this as an output thing, that this is something which the state stores. The parameters are only two, that let's say the ith element for which you are taking a decision for, and the weight available in the bag. So let's assume these are the two parameters that you have. If you have these two parameters, to figure out the number of unique states that you can see in this recursion tree, you will have to figure out the number of values the first parameter can take multiplied by the number of values the second parameter can take. I hope you guys understand that. So what I am doing here, I am saying figure out the number of unique states in the recursion tree. You will have to figure out the different parameters that you have. Once you figure out the different parameters that you have, you can utilize those parameters and figure out how many values the first parameter can take, multiply that with the number of values the second parameter can take, and you can understand how many distinct states will be there in this DP recursion tree, So you guys tell me, the first parameter is I, that is for which element you want to take a decision for. How many different values can I take? I will be equal to 1, 2, 3, 4, so n tak. So you would be able to understand that I can take n values. Okay. Now can somebody tell me how many values the second parameter can take? What is the second parameter? The second parameter was basically the available weight. It will start from W max, that is, at the beginning you had every single unit of weight available, which is W max. But at every step, you are either at least going to reduce the weight by 1 if you are taking some element. Does that make sense? If you are traversing the tree on the left side, you are definitely going to reduce one value, at least 1 unit, because I can assume that every element in this supermarket at least had 1 unit of weight. Okay, it did not have fractional weights, it had natural number weights from 1 से लेकर किसी भी weight तक, right? So you will understand that the number of values the second parameter can take would be equal to the weight max. If you multiply these two values, you get n into W max. So these are the number of states that you can have. Okay, so these are the number of states that you can have, and this is what you see at this point in time. But the problem is that this n can be very large, the number of states can be very large, and you will not be able to, you may be at a position where you are not able to solve the answer. Okay, so let me just wait for a while. If there is any big doubt that you guys have, I would be very happy to answer it. So the argument that I'm trying to build here is that this problem, just because the kind of the problem that we saw here, right? The problem that we saw here, the constraints that we saw here, we got this W max because our bag had a maximum. Weight. If the bag did not have a maximum weight, then you guys would agree that I can potentially have n values for the very first state and so many different values possible for let's say infinitely many possible values possible for the w, right? So you can just keep on saying that I will just keep on selecting, I can just take any decision, and whatever weight it becomes, it will become that weight. But try to look at the problem again. Try to look at the very first 3 points that I wrote at the beginning, right? So let's look at these 3 points that I wrote at the beginning for knapsack problems. It's an optimization problem. In general, it would be exponential time, but there is some constraint which is apart from the size of the problem, which makes the problem solvable in polynomial time. And now let's try to understand that particular sum constraint that I was talking about. Okay, the sum constraint that I was talking about here was that you have this constraint that you can have a bag with a maximum weight, right? The bag has a maximum weight. Does that make sense to everybody? The bag has a maximum weight, and exploiting that particular value tells me that the number of unique states in this recursion is going to be n into w max. Does that make sense to everybody? So what you can see is, just because you had that parameter, that there is a maximum weight for the bag, which makes it n into w max. Cool. Using this, exploiting this constraint, this will actually help us to model this problem in polynomial time. Does it make sense to everybody? I hope it does. Cool. Right. So we have discussed this. We have discussed this recursion tree. We now understand that these are the states that we had, and this tells me the number of unique states in the DP, and which makes the problem solvable in polynomial time. That's great. Now, once this is done, once we realize that there is a optimal substructure there, once we realize there is overlapping subproblems there, that is, there are some unique number of states that you can get in this DP is going to be very very less than the overall states that could have been there. Now you know that a DP solution here would work. Good. Can you guys help me write the recurrence relationship for this DP? And if you guys have seen the first two classes, you would realize that we have discussed that very extensively, how to actually figure out the recurrence relationship for a DP, right? So what do we do? First of all, we figure out the parameters that defines a state. So first of all, we figure out the params that define a state. Then we would have discussed that we want to see what value does a state give. Basically, what is the physical significance of the value? What is the physical significance of the value of the DP state? Once we know that, we can actually figure out which state will give me the final answer, which state will give me the final answer. And then you can figure out what is the element of choice that you have, right? At every step, what is the element of choice? And using this element of choice, you can actually build the recurrence relationship. So let's try to answer these questions that we see and see how we can solve this question for us. Okay. So first of all, the params that define a state, we already discussed that. Look at these states in the recursion tree. Can we figure out what params are required to represent a state uniquely? We would understand that what I that we are taking a decision for, with the value that is available in the box, in the bag till that point in time, these two params define the state for me. Does that make sense? If I have these two params, I can uniquely identify a state for me. Okay, cool. So if I have these two params, I can uniquely identify the state for me. So first of all, the params that I have is the I, for which I am taking a decision, and the weight available in the bag. Second thing, what is the physical significance of the value that your DP state is giving? So you guys tell me. Let's just look at this recursion tree. The value that I am getting at different states. Can you tell me, looking at this recursion tree, what does this value represent? That value actually represents that if you are taking some decisions from the 0th element till that particular ith element, what is the maximum value that you can get? Okay, why I'm saying the maximum? Because you tell me, if I'm taking a decision for the first element, and that actually boils down to taking a decision for the second element, I had two options for the second element. So basically, so you can understand that here I am taking the decision for the first element, I have two options. For the second element, I have again two options, and so on and so forth. At every state, just because you want to maximize your total value, you would want to take a max of the two options that you have. Does that make sense to everybody in the class? To get the final answer, you will have to take the maximum of every option that you have at every state. Does that make sense to you folks? Right. If it does, you will realize that yes, at every state, the value that you are getting would be the maximum value that you can get from taking a decisions from the 0th. If I'm building it from left to right, it would be from 0 to ith. If I'm building it from right to left, it would be from ith to nth. And you guys can actually fall back to the previous two videos to appreciate that we can build these kinds of symmetric problems from both ends. Okay, so the physical significance of the value. So let me try to build it from left to right. The physical significance of that value would be what is the maximum value you could have looted in the let's say, okay, so let's say in the elements from I, from 0 to I. What is the maximum value you could have looted in the elements from 0 to I, in the elements from 0 to I, if the weight that you consumed in the bag was equal to W maximum minus W available, if this is how we go about it. Or let's say if the weight available in the bag, weight still available in the bag is W available. I hope it makes sense to you guys, right? If this is what my physical significance of the state is, can you answer the third question for me? Which state will give me the final answer? The state that is going to give me the final answer is going to be, because the ith, the first, okay, so the state that is going to give me the final answer is going to be dp. I just need to fill these two arguments here, right? So what would be the value of these parameters which would give me the final state? So just look at the problem, just look at what is physical significance. The first parameter I means from 0 to I. So at the end, you will have to take from 0 to n. Does that make sense to everybody? So it would be dp of n without a doubt. The second thing is, what is the weight available that you see is possible, right? If you are building up with the weight available, you can see that at most the weight available should be 0. Does that make sense to everybody? This may not give you the final answer because 0 may not be there at all. So you can actually build and say that the dp of n, and whatever I get, I will take the maximum of it. So let me actually now, rather than focusing here, let me actually build a recursion, and then this thing will be very crystal clear, and how I can actually make it boil down to a single state and not even to a combination of states. So let's just wait for a while, and let me just take the element of choice, build the recurrence, and then we will come back to it. Okay, cool. So yeah, dp of element I with some weight available, right? You want to solve this. You tell me, if I means from I se lekar n tak you have already solved the problem. Okay, if I means you have already solved the problem from I se lekar n tak, now which side will this fall back to? I hope you guys you can able to understand that we can build it from left to right or right to left. Both of them are equally valid. Let's try to do it anyway. Okay, so we have dp of I comma weight available. Okay, now we have two choices. Either I can say that I will pick the ith element, or I will not pick the ith element. These two decisions are mutually exclusive and mutually exhaustive. The moment we understand this, we appreciate that yes, just by looking at these two, I would be able to get the complete answer without any doubt. Cool. The first option that you have is pick the ith element. If I pick the ith element, can you figure out that this dp now should actually boil down to I plus 1? Because I have taken a decision for the ith element, do you understand that I will now, let's say, take the decision for the I plus 1th element? Let's say I'm building from left to right. I could have built it from right to left as well, but let me just say I'm building it from I plus 1. So, okay, so you can do it both ways, Shobit. So if you are picking the ith element, you can either say that I will boil it down to I plus 1, or you can say I will boil it down to I minus 1. No matter what you do, you will get an answer, but the final answer will be different in different two states. So let me just do it with I plus 1, and I will explain you at the end that how we could have done it with I minus 1 as well. Okay, Shobit? Cool. So let's say pick the ith element. If you're picking the ith element, let's say dp of I plus 1. This is what your problem boils down to. And the weight available would become weight available presently minus the weight of the ith element. Does that make sense to everybody? Right. After that, do you understand that this would be the dp, and the value that you're going to get in that state is going to be plus value of the ith element? Does that make sense? Cool. This is one option. The other option was not picking the ith element. If you are not picking the ith element, it will again have dp of I plus 1, because just because you have taken a decision for I, let's now move it to I plus 1. The weight available would still remain w weight available because you are not taking anything, plus the value that you're adding would be 0. Does that make sense to everybody? These are the two choices that we have. To get the answer, I will just have to take the maximum of these two. So I will just take the maximum of these two. This is what will define the solution to me. Now, if this is how I went about the problem, you guys tell me which element will give me the final answer. You tell me which element will give me the final answer. If my dpi is using dpi plus 1, dpi plus 1 will be using dpi plus 2, dpi plus 2 will be using dpi plus 3. Can you figure out which state will be using everything? Can you figure out which state will be using everything? The answer to that would be that dp of 0 would be using everything. Does that make sense to everybody? dp of 0 would be using everything. Now, once dp of 0 is something that is using everything, at the beginning, you tell me what is the maximum weight available that you have. The maximum weight that is available to you would be weight maximum of the bag. The maximum weight available to you would be weight maximum of the bag. Now, if you call this dp with this value, it will compute the values automatically inside, and this will give me the final answer. This gives me the final answer. If I chose to build it from the other way around, I could have just said, I will just write it here so that everybody appreciates in the class. I can just say, otherwise I would have said, if I'm picking the ith element, my problem reduces to dp of I minus 1 because I'm building from here to here. Okay. If dp of I minus 1, this is what my problem boils down to. If I'm trying to solve it the other way around, the value available, the weight available would still be weight available minus weight of the ith element, plus the value would still be value I say add of 0. Okay. If I do not pick it, my dp state otherwise would become dp of I minus 1 weight available plus 0. And if this was how I was defining my dp, can you figure out the state which has the value of everything? Can you figure out the state which has the value of everything? Because I falls to I minus 1, I minus 1 falls to I minus 2, I minus 2 falls back to I minus 3. Which state will have the value of every such state? The answer would be dp of n, comma, weight m. I hope everybody in the class, so I've seen so many people getting confused in this so many times. In maybe different interviews that I've taken, I've seen people getting confused in this. And this is something that you should not be confused if you just understand how you are building your answer. So this would be the final answer in this case, and this would be the final answer in this case. We have discussed it, right? Cool. We have discussed it. To solve it, you can just have two options. You can just do it bottom up or you can do top down. We discussed that in top down, you just have to write a recursive solution. You first take the base case and you just write the recurrence and you will get the answer. In bottom up, you will just start from the base case and see, using the base case, what is the next element that I can compute, and just compute in that order. Okay, I'm not going to write the code because I want to discuss several other things in the class today, but I hope everybody in the class appreciates this. Cool. One last thing. The moment you define your DP in a different manner, the base case also changes, right? The base state also changes with the different ways in which you are taking it. The base case basically means that looking at the recurrence, what is the value? What is the state that you cannot fill by looking at the recurrence? Okay. So what is the base case? Please, people, appreciate it this way. The moment you appreciate it this way, you will never be confused in base cases. Base cases basically means that the case that cannot be defined using the recurrence for us. The case that cannot be defined using the recurrence for us. In this case, can you figure out which case cannot be defined using the recurrence? Because for every state, I am using the I plus 1th value. So can you figure out for which state I plus 1 does not exist? For the nth state. Does that make sense, folks? For the nth state, the I plus 1 value does not exist. Folks, are you with me? I hope you are, right? So one is, for the nth state, this would be the base case in this case. So you would just fill dp of n, let's say weight maximum. That is, you do not choose it, it would be 0. If you chose the nth state, you have two options at the nth state, right? If you chose the nth state, then it would be w max minus weight of n, and the value would be value of n. Does that make sense to everybody? Right. And similarly, for the other case, you will have first as the base case and you can fill it. Cool. Let's now move ahead. This is the first thing that we did. In the meanwhile, let me now bring your attention to another kind of knapsack problem. And then we will try to appreciate, first of all, whether we can solve it greedily or not. Okay. Let me just take you to another knapsack problem. And I would want you guys to tell me whether we can solve it greedily or not. Let's assume this problem that we just discussed is called as 0-1 knapsack. Now let's say I am discussing something which is called as fractional knapsack. What does that mean? That means that let's say you are still a robber, you are still going to a shop to rob something, but let's assume this is some kind of a grocery shop. Okay. And what do you mean by grocery shop here? What is the difference? The difference is again that you have, let's say, different values. You have n items here. Every item has some associated value with it, and with that you can essentially have every item will have a weight also. Okay, every item will have a weight also. Now looking at this array, the only thing that changes is that initially it was 0-1, that you can either select an element completely or you can not select an element at all. Here it's a fractional knapsack, which simply means that you can select any item x number of times, where x is a real number between 0 to 1. Does that make sense, folks? So you can actually take any fraction of any element. The moment you can take any fraction of any element, can you answer this for us now? Can you see if we can solve a greedy? Can we solve it greedily? Think about it for a minute. Right. And yeah, several of you understand that yes, you can solve this problem using greedy approaches. The point here is why you can solve this problem using greedy approach is that you can just start with the bag. You can just start with the item which gives you the maximum utility per unit cost. Okay. So what do? You start with the item that gives you maximum utility, or here the utility means value per unit weight. Okay, that gives you the maximum utility, maximum value per unit weight. Why this will work? This will work because if I am selecting something that gives me the maximum value per unit weight, I am making the most out of that weight. Does that make sense? If I am selecting a value which gives me item which gives me the maximum value per unit weight, I am definitely making the most out of that weight. This is one argument that I'm building. Just because I am selecting the maximum, I'm making the most out of that particular weight that I just gave for the first item that I selected. The point is, whatever value is remaining, whatever weight is remaining for my bag, I can fill that also in the best possible manner because I am allowed to take fractional items. In the previous question, the problem was if I am trying to optimize for this particular weight and I'm selecting an item which gives me maximum weight per unit value, maximum value per unit weight, the problem is maybe I will be left with some weight which becomes a dead weight. I cannot fill anything in that dead weight. This was the problem. Here the point is that you will never be left with any dead weight because you can always fill it with the thing which is going with anything which is the next best thing in a fractional manner. I hope I have made myself clear to everybody that this problem, the problem of fractional knapsack, can be solved greedily. Cool, folks. We discussed that. Let's now move to the third problem of the day that we want to discuss. That problem is called as 0 to many knapsack problem. Okay, let's discuss the third problem now. The third problem is there is another kind of knapsack problem which says 0 many knapsack. Let me define the problem for you guys. The problem is again that you want to select some items which will maximize the value for you and given satisfying a constraint on the maximum weight. But this time around, you can essentially select an item from 1 to infinitely many number of times. Does that make sense? So let's assume the first element had some value 100, second had some value 120, this had 60, this has 40, this has 30, and the weights were, let's say, 10, 2, 20, 25, and 30. Right? Now the point is that you can choose to select any element n number of times. You can either select that element 0 times, you can either select that element 1 times, 2 times, 3 times, n times. Okay? So you can select any element n times. The point here is just because you can select any element n times, the first answer that we discussed would not be sufficient here, right? Because the element of choice changes. Let's just wait for the element of choice. First of all, you guys tell me, can you solve this greedily? You cannot. Think about it, take it as a homework and figure out why you cannot solve it greedily. This is very simple to make an argument for. Cool. Cool. Let's. Okay. So now the problem is that you have zero to many knapsack. Okay. Now let's first of all try to build the recurrence tree. That is how it makes every problem simplified. Let's try to look at the recursive tree. Again, let's say you start with making a decision about the ith element. You again have a available weight which starts with W max, and you again have a value aggregated which starts with 0. Now you tell me the options that I have, the element of choices that I have. Either I will not select this element, that is I will select it 0 times, or I will select it 1 time, or I will select it 2 times, or I will select it 3 times, and so on and so forth. Does that make sense? Just because you have so many different options, let's try to formulate all these states. So if you take it at element 0 times, your problem now reduces to solving for I is equal to 2. Your value aggregated still remains 0, and your weight available still remains weight max. Let's assume you are taking it for the for 3 times. You're taking an element 3 times. What does that mean? That you're again now taking a decision for the second element because you have decided how many times you're selecting the first element. Your value aggregated is going to be value aggregated, that is what is the present value aggregated, plus 3 times the value of the ith element, right? And your weight available would be weight available, which was previously available, minus 3 times the weight of the ith element. Does that make sense to everybody? Shobit, the question here is that you can select any item n number of times. You can select an element 0 times, you can select an element 1 time, select an element 2 times, 3 times, n times. Right? There is no limit on how many times you can select an element. Does that make sense, Shobit? Can you actually figure out for me what is the maximum number of times that you can select an element? You can keep on selecting an element till the time your weight available is still greater than equal to 0. Does that make sense? You can keep on selecting an element till the time your weight available is still greater than 0. Right? I hope it makes sense. Cool. So now we appreciated, we discussed this. This is one way of building the problem. But you see that this is very difficult because you do not know the fan factor. Do you know the fan factor already? You do not know the fan factor. You will have to take a loop and maybe select them one by one. That's still solvable. You can write a recurrence relationship for it, no doubt. But I would want to make you guys understand, look at this problem in a way which is more intuitive and which will make you a lot happier. Okay. So do you want me to look at it in another way as well? Okay. Let's actually look at it in another way as well. So this is one way to look at the problem. This problem can also be looked at in a different manner. Okay, the different manner is this. First of all, you take a decision for the first element. Value aggregated till this point in time is 0. The weight available at this point in time is W max, and you're good to go. Now, rather than saying that you have so many different choices, let's assume that there are only 2 choices. One choice is that you do not select this item. That is, you say that I am not selecting this item. The other choice is that let's say I am selecting this item. If I do not select this item, it would be very easy to understand that I would go to I is equal to 2. My value aggregated would still remain 0. And my weight available would still remain W max. Okay. The other option is that I choose to select it. If I choose to select it, you would agree that my weight available would become weight available minus weight of the first element because I chose to select it. My value would become value aggregated plus value of the first item that we had. But just because I only gave the option till this point in time to select this element once, but I could have essentially selected this element multiple number of times, I would still keep the I of my state equal to 1. Why would I still want to keep it 1? Because I would want to give that choice again, whether do I want to select the ith element or not select the ith element. If I do not select the ith element now, if I reach to this state, do you understand that from the beginning till this state, I have selected the I is equal to 1 times, and now I am moving to I is equal to 2. So I now know that if I wanted to select I equal to 1 times, I will choose this path. If I choose the I is equal to 1 again, would you agree that from this to this, I have already selected I 2 times, and I again give myself an option of not selecting it and selecting it. If I do not select it now, then I move to I is equal to 3, I is equal to 2, because now this state will represent that I have selected I is equal to 1 2 times. If I still select it, that means that I've already selected it 3 times and I'm again giving it a choice. Does that make sense to everybody? Does that make sense to everybody? This is a very, very intuitive way of understanding this problem in a slightly different manner. That at every state, you can either choose to select that element or not select that element. If you do not select that element, it would simply mean that, okay, man, I'm not selecting that element. Let me take a decision for the next element. If I choose to select an element at that point, I am still leaving the scope of selecting it one more time, two more times, three more times down the line. Does that make sense to everybody? This actually in my opinion, would actually make you a lot more happier and would allow you to understand this problem at a much deeper level. Cool. So let me just write the recurrence relationship for this as well. Let's say you have again two states to represent your problem, dp of I and dp of w, dp of I and weight available. You can say that again you are going to take a maximum out of the two choices that you have. What are the two choices that you have? The first choice is that you do not select it. The second choice is that you do select it. If you do not select it, it would make it dp of I plus 1 because I did not select it. Let me now take a decision for the second element, and w max still because I did not select it plus 0. Okay, this is one option. The other option is that if you wanted to select it, you will say again, not go to dp of I plus 1 here, still remain at dpi because I will want to give it chances further down the line also to select this one more time, two more times, three more times, and my w max. So this is w available. Sorry, this is w available. This will not change. In this case, it will change because I've selected it one time, and the available weight would reduce, so it would become w available minus weight of the ith element plus the value of the ith element. Does that make sense to everybody? And if it makes sense to everybody, let me actually define. So I would just want to maybe discuss one more thing which you would most likely not find at so many different places on the internet. Maybe this thing you will, of course, this thing you will find at so many different places, but I just tried to explain it in a much more detailed fashion. But I can maybe take 10 more minutes to explain to you something else which maybe you will not find very easily at different places. Okay. So let's actually try to look at a variant of these problems. And before looking at the variant of these problems, let me actually take you back to the very first definitions, that the very first points that I wrote about the knapsack problems. Knapsack problem is a class of problems in which you are trying to solve some optimization problem. Generally, it is going to take exponential time, but there is some constraint which is apart from the number of elements in the array, size of the problem. There is some other constraint that actually makes this problem solvable in polynomial time. Okay, it actually makes your problem solvable in polynomial time. Cool. So let me try to make you guys appreciate that constraint till this point in time was weight of the bag. Does that make sense to you guys? We were piggybacking on the weight of the bag to solve this problem in polynomial time till this point in time. Does that make sense? Because we were using the weight available as the second parameter, and that gave us fixed number of unique states, and that enabled us to solve this problem in polynomial time. Before actually that, let me explain to you what is the time complexity of this algorithm. Let me give you a formula that is going to help you all across in DP problems. The time complexity in any DP problem, the time complexity in DP problems can be very easily figured out using a way. The way is that you first of all look at the number of unique states and you multiply the number of unique states with the time taken to compute one state. The moment you keep this formula in mind, you can solve the time complexity of any DP problem very, very easily. Okay, how so? So let's look at in this example. So how many states do you have here, folks? How many different states do you have? Unique states. We discussed that we had two parameters here. The first parameter was I. It can take n different values. The second parameter was, the first parameter was n. The second parameter was weight max, because that gave us the upper bound on the second parameter, the weight. So n into w max is the number of unique states. And can you tell me the time that it takes you to solve any state? You are just taking a maximum of two different states. Folks, does it make sense? The time that it takes you to solve one state here is just taking a maximum of two different states, and taking a maximum of two different numbers is just the order one computation. Does that make sense to everybody? So basically it becomes n into w max into order one, which makes it order of n into w max. This is the time complexity of the knapsack DP problems that we discussed till now. Does that make sense to everybody? So this is how you compute the time complexity. Now let's actually come to the second thing that we want to discuss, a variant of this problem, and let's try to look at it. So we appreciate that we were able to solve this question in polynomial time only because of this parameter W max, which helped us solve this. Let me now instead give you a problem where this W max would be too big for you to solve it in n into W max time. Okay, so let's assume that maximum weight of the bag is very large. So let's assume, let's say weight maximum is of the order of 10 power 9. Okay, weight maximum of the box is, let's say 10 power 9. Number of elements in the market that you are trying to loot is, let's say 10 power 3. You guys tell me, can you solve this problem now in the approach that we just solved? Can you solve this problem in this way? We cannot. Do you appreciate why we cannot? Because the time complexity of our present approach was n into W max, and that would make it 10 power 12. And can we solve a problem which takes 10 power 12 iterations? We cannot. So this kind of a problem we will not be able to solve based on the things that we discussed till now. So what is the fundamental thing that we can see here? The fundamental thing that we can see here is that the parameter on which we are piggybacking is no longer kind to us. We can no longer piggyback on that parameter to solve this problem, right? So now let's try to look at some other parameter on which we can piggyback and solve this problem. Let's assume the other parameter on which we can piggyback is this. The other parameter was the value of any item. They are telling us the value of any item is going to be less than equal to 10 power 3. Now please appreciate, this was also a possible parameter, right? But we chose to make that parameter as a value. We chose this weight max as the parameter in the previous solutions. We piggybacked on this, but here this will not allow us to piggyback. Can't piggyback on this now. If I can't piggyback on this, let me try to piggyback on something of this. Folks, is it making some sense? Knapsack problems basically looks for a parameter which you can piggyback and solve that problem in polynomial time. Here, let me try to piggyback on value of elements and let me try to solve it somehow. I'm sure that you guys would be getting some sense of it, and once I complete it, you would be able to appreciate it completely, and you would not see this being talked at different places very easily. Cool. Let's move ahead. Okay. Cool. So the value I is less than equal to 10 power 3. So you tell me, folks, if I am solving this problem, what is the maximum value that I can hope to get? Let's assume there was no constraint. The upper bound to a value, maximum value, upper bound to these maximum value that I can get, value aggregated that I can get, would be just the summation of all the values. Does that make sense? If I just do the summation of all the values, that can be the maximum value that I can get. Does that make sense, everybody? I cannot get a value more than it because I'm selecting every single item. Let's assume this is 0, 1 knapsack. I am selecting every single item, and the maximum value that I can get is summation of all the values, right? Now, let me define my problem this way. The recursion tree still looks the same, that you have I, you have a value aggregated, and you have a weight available. But this time around, I am not using these two things to define my state, but instead, I am using these two states to define these two parameters to define my state. So my state would be something like this: dp of I, comma, the value aggregated. Okay, and the answer that this is going to give you is going to be, let's say, what is the minimum weight that you will have to fill in the bag to get value is equal to value aggregated from 0 to ith elements. You would want to figure out the minimum weight. Here you do not want to maximize anything, you want to minimize the weight, because you are filling weight now, assuming that you have the value filled. Does that make sense to you, folks? So you are filling weight now. So what is the minimum weight that you will have to fill in the bag to get a value of value aggregated from elements 0 to I? How will I write my recurrence? I will again write my recurrence like this only: dp of, let's say, I, comma, value aggregated would be equal to, I have two options, either to select that element, not to select that element, the same options I have. If I select ith element, my problem will boil down to dp of I minus 1 because I have taken a decision for the ith element. Now I have to take a decision for the I minus 1th element. The value aggregated that I have till this point in time, folks, the value aggregated till this point in time would be value aggregated minus the value of the ith element. What does that mean? I am essentially trying to see whether this value I would be able to aggregate or not till the end. The moment this becomes a 0, I will be able to aggregate. Folks, is it making some sense? This is one option that you can select the ith element. The other option is you cannot select the ith element. In that case, you would be dp of I minus 1 and your value aggregated will remain the same. Now I have purposefully left this problem a bit open-ended. I would want you guys to spend some time, think in that direction, this direction, and see how you can solve this problem by piggybacking on the summation of value aggregators. Folks, does it make sense? Let me just give you one hint. Here, maybe the final answer will not be given by a single state, but you will have to maybe traverse on a collection of states to figure out the final answer. This is just a hint that I gave you. Think about it yourself, try to solve it. If you guys are stuck in this specific problem, you can reach out to me over LinkedIn. Yes, you will have to minimize the weight here because the point is that you are actually defining a problem. If I have this much value, what is the minimum weight that I would require? This is still an optimization problem. You would still want to optimize on the maximum value with the minimum weight. Does it make sense, folks? In the previous approach, we were trying to do maximizations of values. Do you understand? Here, we would want to do minimizations of weights. Folks, does it make sense to everybody? Here we are going to take minimizations on weight because I am getting this value. What would be the minimum weight that will allow me to get this value? This is what makes sense, right? You would not want to define your problem saying that what is the maximum weight that would be required to get this value, right? Instead, you would want to say, what is the minimum weight which can allow me to get this value? Does that make sense to everybody? Abhishek, does that make sense to you? Right. So you would want to figure out the minimum weight that can give you that answer, that can give you that value. Cool. Thanks a lot, everybody. I hope you guys enjoyed the lecture.
Okay, let us begin with the very first session on dynamic programming of 21 days of code. This is not going to be a theoretical session. I'm just going to solve 3 problems that you guys had suggested over the LinkedIn page. Let me just give a brief about what DP is. DP is very similar to what recursion is or divide and conquer is, so as to say. Basically, when a solution to a problem can be achieved by solving the same problem with smaller inputs, and then you solve the original problem by combining the outputs of the smaller problems, that is what is known as DP. In DP, there are 2 important properties: that the problem should be overlapping. What is meant by overlapping is that one state can be reached from multiple other states. And how to identify a DP problem? The best advice will be practice as many DP problems as you can. It's only practice with which you will easily be able to identify that, hey, this is a DP problem. And then in a DP problem, the different possible states are almost fixed. As far as my experience goes, no more than 8 or 9 different states exist of DP. Okay. Akhil, how to find number of states of DP is also dependent upon the question, and the intuition gets clear to you only when you practice. There are some very nice articles about DP that are present on Code Forces or Top Coders, so do read them. They will also help you identify what are the possible DP states that are generally asked. Okay, but without practice, you won't be able to identify that, even if you have studied a lot of theory. Okay, so for DP especially, I suggest you to solve as many problems as you can. Okay, so today we will be taking one problem from simple array DP, one from 2D string DP, and let us say one from greedy or DP. Okay. So one question is by Debarun. The difficulty that I face most about DP is that how to convert a memorization solution to a bottom-up solution. That's a very good question, Debarun. What I personally do, since the time I have started solving DP problems, I always solve them from beginning in a bottom-up fashion. I don't do it this way that, hey, first I code a recursive solution, a top-down solution, and then memorize it and then convert it to bottom-up code. I never do that. I always try to create DP state in such a way that I can directly start with a bottom-up code. As I told earlier, there are no more than 7 or 8 popular states of DP. So do read those articles that are mentioning that, okay, what are the different possible TP states, and then things will get clear to you. Okay. So what I will suggest to you is, when you are solving a problem, solve it anyways, and then at least see the solution of it in a bottom up fashion as well. Okay. So because when you have seen the solution to it in a bottom up fashion, then you can remember it for always. And then when a similar pattern comes, you can directly apply that. Okay. So let us start with, so first people ask us to solve the longest increasing subsequence problem. Okay, let us do that. So this is the longest increasing subsequence problem, and let us solve it. So the problem says that we have to find the longest increasing subsequence of a given array of integers A. So basically we will be given an array of integers. The length of the array will be almost 2500 in worst case. And we have to find a subsequence of an array in which the elements are in strictly increasing order. Okay, strictly increasing order means the next element should be greater than, not greater than, equal to, right? Okay. And as this is a subsequence and not a subarray, so it need not be what we say contiguous. So that is also fine. And we are only asked to find the length of the longest increasing subsequence and not generally what the exact subsequence is. So we are just asked that what will be the length of the longest increasing subsequence. For example, in this array A, we can choose 1, 2, and 5. So this is the longest increasing subsequence. 1 is smaller than 2. Similarly, 2 is smaller than 5. And what is the length of this subsequence? It is 3. So we are just asked to return 3. By the way, this is a very popular problem. This is a very well-known problem. And there are two different kind of solutions possible to it. This problem has one order of n square solution that is quite easy and is based upon what we say dynamic programming. And there is also an order of n log n solution to this. Okay. This is based upon what I think it is more like binary search solution. Okay. As today's class is a DP class, I won't be discussing the second order of n log n solution, but I can just send you guys the link to resources where you can study about that. Okay. But do try this because the binary search solution, once it hits you, is very good for you. Okay. Or actually, let us try to solve it in order of n log n way as well as today. Okay. Let me answer what the other questions are. How much time should I give on TP? Like 1 month? Akhil, yes, 1 month. I mean, like 1 month of solving only TP problems is fine. I mean, like it depends upon how many different problems you solve of different difficulty. If you keep on solving easy problems, you are never going to improve, right? Try to solve those problems that you were not able to solve initially. Try to grow with every problem. Okay. And other than practice, any other thing can we do? Harsh, I mean, like for DP, your mind works like a machine learning model. The more practice you will give to it, the more accurate it will get with DP. Okay. I mean, like practice is the best thing. And you see a solution, always implement it, and then also read. I mean, like then also make sure that your mind is totally able to visualize that solution. Okay. Okay, let us start with this problem. So we are asked that, hey, we are given an array A and we have to find a longest increasing subsequence of this array. Awesome. So how can we do that? Okay. Suppose I know that, okay, I want to see that, hey, can I include, let me actually rewrite this array again. Let me rewrite this array. Okay. 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 So now at every iteration, I will try to see if I can include that particular element, in my longest increasing subsequence. Okay. Let us see how we can do that. So suppose, can I include 0 in a subsequence? I can include this 0 in a subsequence only if there already was a subsequence in which the last element was less than 0, right? Okay. Is there any subsequence before it that has the last element less than 0? No. That means this 0 will create one more subsequence, will create another different subsequence of size 1. Okay. Then I go to the number 8. Now I try to see if I can have a subsequence that can have 8 as the last element. When is that possible? That is possible only if before this I had a subsequence that had a number less than 8 as the last number. Okay. What are the subsequences before it that have a number less than 8 as the last number? This is a subsequence that has what we say 0 as the last number. So I can put 8 ahead of it. So what will be the length of subsequence that will be at 8? It will be 1 plus 1, which will be equal to 2. Great. Now I go to 4. Now I will try to include it. When can I include? I can include it only if uh, there was a subsequence before it that had a number less than 4 as the last number. There is only one subsequence that was ending with 0. So the answer will be 1 plus 1, so which will be 2. Okay. Then you go to 12. Now, how many subsequences are there before this number 12 that end with a number less than 12? There are 3, right? This subsequence ends with a 4. This subsequence ends with a 8. This subsequence ends with a 0. So, either I can add 12 after the subsequence that ends with a 0, or I can add 12 at the end of a subsequence that ends with 8 or that ends with a 4. As we see that this is the largest length of a subsequence that ends with a number smaller than 12. So I will add 12 after this. So my answer will become 2 plus 1, which is 3. Now I go to 2. This is the only subsequence. So my answer will become 1 plus 1, which is 2. Now I go to 10. What are the subsequences? This is a subsequence. This is a subsequence. This and this. Out of these, the largest is 2. I mean, like the largest one has a length of 2. So my answer will become 2 plus 1, which is 3. Great. Now I go to 6. What are the subsequences that have a number less than 6 as the last number? This, this, and this. Out of these, the length of the largest one is 2. So this one will also become 3. Great. Then I go to 14. Then I will see here all these subsequences have the last number as less than 14. Then out of all these, which one has the smallest length? Which one has the largest length? This has the largest length of 3, right? So my answer here will become 3 plus 1, which is 4. Okay, I hope now the intuition is clear. So what we can do is we can create a DP table. Let me just write the size of A. Then I will create a DP table of the same size. What is the value of the first index going to be? The value of the first index is always going to be 1, right? So I can say dp0 is 1. That is the base case. Now my answer is initially it is 1. Then what I do, I say for int I equals to 1, I less than n plus plus I. Now I try to find all those dp states in which the last number was less than the current number. So what I will do, I will say for int j equals to 0, j less than I plus plus j. If array j was less than array I, that means the increasing subsequence at that number ended with something lesser than the current element. Then I can say that dpi is equal to max of dpi, comma 1 plus dpj, right? Basically the length, what was the length of the subsequence at that particular number plus adding the current element. Okay, great. So now my answer will become max of answer, comma dpi, because I have to find the largest length. And finally, I can return answer here. What is the time complexity of this? This is order of n. This is also order of n. So the time complexity will become order of n square. I think the answer should be correct. Let us test it. What is the issue? Is it less than or is it less than equal to 0, 4, 6, 9, 13, 15, 0, 4, 6, 9, 11, 15? Return an integer longest increasing subsequence or unique, and in which the subsequence is as long as possible. Okay. Here I am returning 14, but the expected output is 15. For int j equals to 0, j less than I. Max of dpi. Initially it will be 0, comma 1 plus dpj. That is also fine. Is it less than or is it less than equal to? Because it says find the longest increasing, find a subsequence of array in which the subsequence elements are in strictly increasing order. So that means the elements are always increasing. I mean, like equal to is not allowed. But in this particular question, the answer is coming out to be 15. Why will that be the case? That will be the case when current I equals to 1, I less than n plus plus I say if aj is less than, let us say, what if aj is less than equal to, when what will be the output then? Then also my question returns 14. Okay, so that is not the issue. There is some other issue then. I created a TP of size n. Initially my answer is 1. Then I say for int I equals to 1, I less than n plus plus I. Okay. Then I iterate over each the element of array I. And then I run a loop from j equals to 0 to j less than I. Okay. That is also perfect. Then I say if array j is less than array I. Okay. Then I update my TPI, so which is this TPI, to max of TPI comma, I mean like what was the value presently there, and 1 plus TPJ. So that is also fine. But the answer here is 15. Let me try to debug this code as to why this is happening. Let me say that I output my TPI at each stage. This is coming 14 and 14. This is correct. So this should be 14 and 14. That is perfectly correct. And I'm not getting 14 anywhere else. So that is also fine. But I am getting this as 0. Okay, now I got the issue. Initially, the stage of dpi will be 1, right? So initially, each of the element will be dpn comma 1. That I have said the default value should be 1, right? If it is the only element of dp, then the answer should be 1. So I always had actually off by 1 error. I forgot that. So I mean like if that element is the smallest element, like in the case of, suppose, what if say that -1 would have been here, then -1 would have been the single element. There would have been no element smaller than this, right? So the DP state here should be 1 and not 0. So now we will be correct. Correct. So we got this as well. And let's move to the next question. That was wildcard pattern matching. Actually, there are two questions like that as far as I remember in interview bit. That is the regular expression match and regular expression match 2. Which one do we want to solve? Let us try to solve the regular expression match 2. Okay, let's try to solve this. Okay, so I'm not sure if any one of you has ever seen regex before, but what regex allows you to is basically to find all the strings in your directory that match a particular pattern. Okay, so basically we are asked to implement a very similar function to how regexes would be working, where the possible values in a regex are fixed. Like here we are told that we have to implement a regular expression matching algorithm that can support a dot and a asterisk. What dot means, a dot can match any character, any single character in my in the whole string. So basically, let me say that, does dot match a? Yes, that is true. Okay. Does dot match b? Yes, that is also true. But does dot match a? No. Okay, so a full stop can match only one character, any character. Okay, a full stop can match one occurrence of any character. Okay, then the second unique character given to us is asterisk, and asterisk can match 0 or more of the preceding element. What it means is that, suppose we have a star can match a, it can match a, it can also match a, and so on. Okay, so this is what asterisk means: one or more than one, zero or more than zero occurrences of the previous character in my regular expression pattern. Okay, so for example, does this string a, does this pattern match a? No, because though this a is equal to a, but then there should also be a second a, but it's not present in the string. Okay, so the very first one is a string, the second one is a pattern, but the same thing holds. This matches. This doesn't match because the string is AAA, but the pattern is only two A's. So it doesn't directly match. Now, double A, does it match A star? Yes, it does. Why? Because A star is equal to single A. It is also equal to double A. It is also equal to triple A, and so on. So, does AB match star asterisk, dot asterisk? it does. Why? Let us say, what can this dot represent? This dot can represent A. This dot can also represent B, right? And similarly, this can also represent C. That means, what can dot asterisk represent? Dot asterisk can represent AA. It can also represent BB. It can also represent CC, right? So that is why dot asterisk is true, right? Matches 0 or more of the preceding element. Yeah, preceding element is a full stop, so it can match precede 0 or more than 0 occurrences of previous character, which is anything. So it can match 0 or more occurrences of anything. So basically anything can be A, so it will match A. It can also match AB. It can also match AC, and so on. Okay, cool. Now let us try to solve this using dynamic programming. So we are given a string. Let us say that this is the string and this is the pattern. Okay. Now let us try to, I mean, like whenever a string problem is given to you, there are multiple string problems like longest, I mean, like even any 2D array DP problem, you have to, I mean, like normally what happens is that, or even longest common subsequence problem as such in strings. So what you always do, like let us say that we have a string like A, B, C, D, A, and also another string like B, C, E, F, G. Suppose you are given two strings and you try to apply a 2D DP problem, you always try to apply 2D DP in the form of prefixes. That what is common between the prefix of the string A up to index 4 and string B up to index suppose 2. Okay, you always try to compute this. What is common between the first string for up to index X and the second string up to index Y? That is the common pattern in all the 2D DP problems. Adil, yes, a star can match an empty string also, right? I think it should be. I'm not really sure. Let me see. Can star match an empty string? But I think star is, I mean, like if there is only a star, then that means there is no preceding element. Okay, so Adil, if there is only a star, that means there is no preceding element. Then the pattern is invalid actually. Okay, because a star is valid only if there is a preceding character. Okay, so I think then the string, then your pattern will actually be invalid. That is what I hope, but let us see. Okay, now, so I will like following this pattern, we will try to create a DP state of two things. That means string till I satisfies the pattern till j. Okay, so I will try to create a DP state where I will say dpij represents true if the string till index I satisfies the pattern till index j. Okay, ठीक है. Always, I mean, like this is one suggestion. I mean, like whenever you are trying to solve a problem using DP, try to represent your DP state in some English sentence. Okay, after you have represented an English a DP state in English sentence, then you can easily find what we say. I mean, like DP. I mean, like the state relations. Which states will it depend upon? Does A match C star A star B? Yes, it actually does. Why? Why? Because there can be zero occurrences of C. Okay, because I mean, like AAB is nothing but zero occurrences of C. Then two occurrences of A and one occurrence of B. So then it will match. Because a star can also represent zero occurrences of the previous character. So C star will basically just change to an empty string. So that is why it will satisfy. Okay. So now I will try to create a Boolean DP state. How can my DP state be? Let me say that the length of my string is n, and my length of the pattern is p dot size. Okay. Now I will try to create a 2D DP matrix. So I will try to create a DP matrix of vector of bool, I can say, because I only have to represent true or false DP, which will be having number of rows equal to n plus 1. Why n plus 1? While doing DP problems, I personally like indexing by 1 to avoid I mean, like out of bound array checks. Okay, that is why I always create a DP array of size n plus 1, and this will be a vector of pool of size m plus 1. For those who are not familiar with what we say the C++ syntax, this is creating nothing but a DP matrix of n plus 1 cross m plus 1 dimension. Okay, this is doing nothing but this. Great. So will okay, let us say that let us talk about two strings. And let us say that we have a string like this, and this is my pattern. Okay, does nothing match nothing? I mean, like when there is no nothing in the character and nothing in the string, does nothing match nothing? It does, right? So what I can say is BP00 is true. I mean, like nothing matches nothing. So if I talk about indexing, I'm starting one base indexing. So 0 will be here, 1, 2, and 3. So basically 0 is representing does nothing match nothing. Okay, great. So now we have taken care of the base case. Now I will try to solve the whole question. Okay, and let us take care of other scenarios as well. The others will always be false. Now I will try to see if the string till index I matches the pattern till index j. Now, what are the different scenarios? The very first scenario is character at index I, at string I, is equal to character at pattern j, right? Okay. First of all, before that, let us take care of the special characters in the pattern, because that is where an issue can happen. Okay. So I can say that if pattern j minus 1 is equal to dot, then I will handle it separately. Else, if this pattern is b, right? Yes. If bj minus 1 is equal to dot, then I will handle it separately. Also, if bj minus 1 is equal to, what do we say, a star, then also I will handle it separately. Else in this case, pattern j is a character, is an English alphabet. So that means it should match the si, right? It should directly match the character at string at ith index, right? Okay. So that means I can say that if string I minus 1 is equal to pattern j minus 1, then only I can say tpij is equal to 2. Uh, sure, Adil, I will try to draw it after I have coded it, and then I will try to rerun with a test case. Okay, cool. Acha. So now once the character that I'm trying to match in the pattern is not a wildcard character, then that means I can only match it with a character, right? Why? I can match this A of the pattern with only an A of the original character, correct? I mean, like I can match this A only with an A from here. Is that correct? So now let us try to see. So that is the one thing. Now let us see what we will do if bj minus 1 is equal to a full stop. If it is a full stop, then what I can do? A full stop can match with one occurrence, with exactly one occurrence of any character. Let us assume that the pij will be equal to nothing but bp of I minus 1, k minus 1. What this means is, let us say, I mean, like the jth character of pattern matches uh, matches ith character of string. Suppose if the jth character of the pattern matches the ith character of the string, then basically I have to see if whatever the characters were there in the pattern before the jth character match whatever the string was there before the ith character. Okay, nothing else. The problem becomes interesting if we are taking the wildcard character into consideration, right? Because wildcard character can actually match zero or more than one occurrence of the previous character, right? Okay. Now let us try to see how we can do that. First, we try to find that what is the character that came before P. Okay. What is the character that came in the pattern before this star? What I mean is that for this case, it should return me a C. For this case, it should return me a full stop. For this case, it should return me a full stop. Similarly, for this case, it should return me an A. Okay. What I can say is that I think actually the previous element with the first character, right? Yeah, it will always be the previous character. I'm like, we assume that the patterns are defined. So I can say that character, previous character is equal to what we say, the B J minus two. Okay, okay. So what are the cases now? The first case is that if the string at ith minus 1 is equal to the previous character. What does this mean? This means it matches one occurrence of the preceding character. Okay, so what the problem reduces to, the dpij will be equal to nothing but dpi minus 1 j minus 1, because it has matched one occurrence of the previous character. Okay, awesome. Then what are the other cases? The other case is that it is not equal to the previous character. Then that might happen that ai minus 1, it might actually happen that if the previous character is equal to dot, if previous character is a full stop, I mean like in this case, the previous character was a full stop. So that means it will definitely match it, right? In that case, it will definitely match it. So in that case, I can say that dpij will definitely be equal to dpi minus 1 j minus 1. That thing is clear. Then I will say else if a minus 1 is equal to the previous character, then also this is correct. But is there any other case in which this can be true? In this case, PPIJ should be false, right? Because it should not match with anything else. Else DPIJ should be equal to false, right? Can it match with something? What if there are multiple C's and then there is a star? Let us take care of a case like, let us say that there is a C, there is a star, and then I have this C, 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 C. So now when I will be computing this and this will match. Now when I will be computing this and this won't match, okay? Then when I will be computing this and this will be equal to dpi minus 1, this matches till this is also true. When I will be computing this and this dp state, then I will get this is equal to this matches this, which is false, right? This can also match this. So actually, I should return dp else if a minus 1 is equal to the previous character, dpij is equal to dpi minus 1 j, because this will take care of the second occurrence of it as well, right? Take care of multiple occurrences. I mean, like, star can match multiple characters. This thing will take care of this, right? Am I missing anything else? And finally, I will have to return dpnm. But is there anything else that I seem to be missing? So I can say that if there is a full stop, then that means the particular characters definitely match, and then the only thing reduces to a smaller sub problem. So that is fine. If it's an asterisk, I'm like, let us take care of this case at the end. Else, I'm like, both are English characters, then they should directly match. There is nothing better that we can do, right? Because there is an English character there's an English character there. So then they should definitely match. So dpij will be equal to actually dpi minus 1 j minus 1. Why? Because these characters definitely match, and whatever came before this should also match whatever came before this. So this will be the state here. Now let us take care of this important thing. If the previous character is a full stop, then it will directly match. It will definitely match, right? Yes. Okay, else if a minus 1 is equal to the previous character. Else if a minus 1 is equal to the previous character, that means these both are matching, then this problem reduces to, I'm like, multiple occurrences of that, right? Yes. And okay, suppose then I am saying dpi minus 1 j. Okay, this matches this. So let us actually try to create the dp table for this thing. This cc matches this c star, Now when I try to match this thing with this thing, I will say that this C matches this C. So the problem reduces to if this particular thing matches this particular thing. That is true, and then it will be true. Now when I say that if this matches this thing, okay, now this thing is matching this thing, so that is good. And now I will try to check if this thing is also going to match this thing. But then here I will be having an issue. How should I make sure that this is true, right? So I should make sure that if there is a previous occurrence of a character, then that can also be a zero, right? An asterisk can also be a previous occurrence of a null character, because this asterisk can also represent that there was no occurrence still here, right? Yes. Then dpij will be equal to dpi minus 1 j minus 2. If the previous character is a full stop, that is correct, but that can also be a previous occurrence of nothing. So that is true, then that is true. What are we missing here? This particular case is a very difficult case to handle, so as to have all the cases. The bj minus 2 will be the character that was just preceding the asterisk, right? And that character can be a full stop. That means it should match with any character, okay? But I might or might not want to match it, right? If I try to match it, if I try to match the ith character of string with this full stop, then the problem reduces to this problem. Or I might not like to match it. If I don't like to match it, then the problem reduces to dpi j minus 2, right? J minus 2 will make it zero occurrences of the pattern of this character and the string till now. This makes sense. Okay. I now in this case I say if a minus 1 is equal to the previous character, then either I will like to match it, and then the problem reduces to this, or I will not like to match it, right? Or I will say that I don't want to match it, or this is equal to dpi of j minus 2. In that case, if we take care of this string, this problem will be equal to either I match this C with this C, then the problem reduces to dpi minus 1j, which will be equal to matching this C with this C star, okay? Or if I match this C, or this reduces to dpi of j minus 2, which will be false. Now when I try to match this and this, either I will match both of these. If this is equal to this, the problem reduces to dpi minus 1j. dpi minus 1 will be this and dpj will be this. How can I match this? I should somehow make sure that this is true, right? I think that is the only case that is left. I mean, like, if we match this, how should a C star match a C? Because this can mean a one occurrence of C. So as this matches this, the problem can also reduce to matching dpi minus 1 j minus 2, right? Or dpi minus 1 j minus 2. That will be one thing. dpi minus 1 j minus 2. Why this? This will mean this is non-occurrence of this. This is the second occurrence of this, or more than second. This will means this was the only occurrence of it. Okay, and this thing will mean what? This thing will mean zero occurrence. Correct. Now this should be correct. Now the only question comes: can our pattern be something like this? C star 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 star. Then I can also say that while first let us say that can that case happen? Wait a moment. And previous index is equal to what we say j minus 1, while previous index is greater than equal to 0 and pattern previous index is equal to star. I will try to minus minus previous index. So now my previous character will be nothing but b of previous index. Now if the previous character is a full stop, the problem reduces to either I will match it. Now this j will be nothing but, I think let us actually first try to see if what all cases does it pass. Let us then try to see. So we are we are failing at this case. And why? Because this is a zero occurrence of this and this should match, right? And A, B star C means zero occurrence of this. So this should return true. Let's actually try take this case and then see how we are going to create a string. So our 2D table will look like A and this will be C, and then this will be A. Just let me declare a 0 0 as well. This will be a A, this will be a B, this will be a star, and this will be a C. Does an empty string match an empty string? Yes, it does match. Now I try to see if all rest are 0. If I try to see does A match A, this will go into this particular scenario, right? Does A match A? This will be the scenario when AI minus 1 is equal to BJ minus 1. So this will be nothing but equal to this. So this thing will become 1. So that is fine, right? Now the problem is, does A match A comma B? No, it doesn't, because B is also a character and B is not equal to A. So this will not match. Then the question is, does A match A B star, right? So here we will try to see that we have a star, we have an asterisk here. So the previous character is a B, Yes. We go into this case, else case. Correct. We found where the issue is. dpij is either equal to dp of I minus 1. Okay. So I can match none occurrence of that. I mean, like, then it will be equal to dpi comma j minus 2. What it means is that it will only match 0 occurrences of previous character, right? And it should match the 0 occurrences of the previous character. So now this particular case should be correct. Let me take it as a custom input. Yep. So that case we have handled now. That thing is perfectly correct. This can only match 0 occurrences of the previous character. This means this will match dpi minus 1j, which will match more than one. I mean, like, first or second to greater than 2, greater than equal to 2 occurrence of the previous character. This will match 0 occurrences of the previous character, and this will match the first occurrence of the previous character, only one occurrence of the previous character. Now this makes sense, but if there is multiple stars, then it might fail. But first we have to see if there can be multiple stars, right? Rest all should be fine. Yes. And now the question is, will it pass submit case? Can there be multiple stars together? There should not be, but can there be? I mean, like, it's not specified in the input. Let's try to submit it. A, B, C, D is not matching A dot star, C dot star, and this. Interesting. What are we following? Here we have told DPI minus 1. Okay, we have taken care of this case. We have also taken care of this case. We didn't actually improve this, right? This was the DPI minus 1, J minus 1 means one occurrence of the previous character. Okay. DPI J minus 2 means more than one occurrence of the previous character. This can also be 0 occurrences of the previous character, right? Or not. If previous character is equal to this, then the problem reduces to either I will match the previous character with this, then that is fine, or I will reduce the problem to matching this with something else. Let us try to take this case and then see where we are failing. A, B, C, B, C, D, and A dot star, C dot star D. In this case, this dot star is representing this B, and this dot star is representing this B and C. Okay. B, if it is a dot, if the previous character is a dot, then it can match any number of previous characters, right? Yes, then it can actually match any number of the previous characters. So then we just have to find one of the previous indexes where it can match. So that means this is equal to another order of n loop, right? This will be another order of n loop where I try to see if anything matches till here. I mean, like, if there is any part of this substring till here that matches this particular index, because baki sabko because other things I will just satisfy with this stuff with this full stop. That makes sense. So the only question reduces to this, that if there was any star here, right? So then the answer will be to false, let us say. And I can say that for int I equals to 1, I less than, let us say I is equal to 0, I less than I less than what is my current character, I less than for int L is equal to 0, L less than I plus L. That means if there was any character where dp of L k minus 2 was true. So was n is equal to tp or equals to tp L comma j minus 2. What I mean by this is, was there any pair like this, that hey, I mean, like when I'm trying to match this ABCBC with this thing, okay, I will try to see if there was any pair that matched till here in this particular string. After that, everything I will match with a full stop. Okay. So TPIJ will be nothing but was any. This has increased my time complexity, but hopefully should satisfy this case, right? This should satisfy this case. Correct, it does. So now, is there anything I'm missing? Because then I haven't still found that if there can be multiple characters. Interesting. Can there be? First, let us try to submit it and then we will know. Let's first try to test and then we will submit. Hmm. Am I missing any other case? I don't know. Cool. I got it correct. There is not a case of any character, any star, any multiple stars together. But I mean, like, I hope you guys were able to find, I mean, like, how we actually found the approach. What were the different test cases that we had to see? Okay. And still we missed out on some of the edge cases. Okay. I will take up the doubts on this question as well as at the end. But let us solve one more question for the day that people had requested, and then we will take on doubts. Okay. What is the next question? The next question is the max sum path in binary tree. Let us do that question and then we will take the doubts. So in the max sum path in binary tree, we are given a binary tree that is rooted, right? I think we are given a, yeah, we are given a tree node. So I mean, like if you are given a tree node and then it's a DP problem, that is still an easier problem. Why? Because you know the root of the tree and that helps you in some things. So we are given a binary tree T and we have to find a path in the tree of the maximum sum. Okay. And the path can start and end at any node. So by the way, I mean, like, what is the definition of a path? A path is a sequence of nodes such that no node is repeated more than once. So there is no cycle. It's a simple path. Okay. So now let us try to take care of, I mean, like, let us see the examples first. In this example, the largest path starts from this 2, goes up to 1, and then comes down to 3. So the weight of the path is 2 plus 1, which is 3, plus 3, which is 6. So 6 is the answer. In this case, what is the maximum sum path? The maximum sum path is only this node minus 10. Okay. The maximum sum path is nothing but only this node, which is minus 10. Okay. Acha. Now let us try to see that, hey, let us try to see, can we include a particular node in the path? How can we know? I mean, like, what will be the weight of the path if we include that node in the path? Okay. If we include this node in the path, that means either I will have a path from the left side that will join it and a path from the right side that will join it. What I mean is that suppose there was some tree like this, that here is a 1 and here's a 2 and here's a 3, then here is a 4 and then here's a 5. Okay, so when I try to include the upper wala 1 in my path, then I will join it with one path that was coming towards upside from the left hand side. What was the weight of that path? That path was 3 to 2 with having a weight of 5. Similarly, I will also join it with a path that will start at 4 and will end at 5. That will only be in the right hand side of the subtree. This is also a very popular problem, by the way. So uh, I will also join it with a path that is from 4 to 5 and having a weight of 9. Okay, suppose the path on the right hand side, these nodes were -4 and -5. These nodes were -4 and -5. Would you ever want to include these nodes in the path? No, right? Why? Because their sum will be less than 0. And that will be bad for me. I mean, like, I don't want to subtract anything from the path. That is a very bad thing for me. So I will always add the maximum path on the right side with weight greater than equal to 0 and the maximum weight path on left side with weight greater than equal to 0, because otherwise it's going to reduce something from my weight, so I don't want to do that. So let me say that I can make a recursive function that will return me the maximum weight of the path from the left side node and the maximum weight of the path from the right side node. So what I do is that a max path node, which is past a tree node. Okay, in this case, I always try to write the code along with the solution because that makes more sense. I will say, like, the base case is that if a is null, in that case I can just return 0 because there is nothing, it's a 0. Okay, else what I will try to do, first thing I will try to find what is the maximum path on the left hand side, which will be equal to max path node on a left. Similarly, I will try to find the right path, which will be equal to max path node on a right. We will always try to have the paths have a weight greater than or equal to 0, right? So I can make it the left path is equal to max of 0 comma max path node of a to left, and similarly max of 0 comma max path node a to right. Interesting. Now what should I return? I should return the value at a plus left path plus right path. That is the maximum path weight that will end at my current node A. Correct? Great. So that thing makes some sense. In fact, if I know this thing, then I don't need to do anything else, right? I can just paste this thing here. I don't need a separate function as well. And I think this should work directly. Oh, this is XPath sum now. So, and then let's try to test it. This doesn't work. Why doesn't this work? Given a binary path tree, we have to find the maximum path sum. The path may start and end at any node in the tree. Okay. The number of nodes are 10 to the power 4, so the integer overflow will never happen because the maximum path will be 10 to the power 7 something, so that is fine. If a is null, I'm returning 0. Here I'm returning something very big. That is also not going to happen. Interesting. A eval plus left path plus right path, right? That I am not doing wrong. That is correct. If left path is this, I have to say max of 0 comma this. I think I did return correct, right? I think yes, this was an addition issue. What happened? The expected return value is 7347. Okay. And I'm returning something 93,096. Okay. If A is null, I return a 0. Else I try to find what is the max path sum on the left side. Okay. And I also try to find what is the max path sum on the right side. Okay. And then I return the value at that plus left path length plus right path length. That also seems to be fine. But why my answer is coming as wrong? Can I have a path from up to down? Yes, I can have that. And what I will return? Yes, I got the issue. What is the issue with this is, suppose your tree is like this, then what we are doing wrong is this thing. We can't have it in this function. We should have another function which says int max path ending here. Okay, and max path ending here is this, given a tree node value at A. So now I try to find what is the maximum path in both of those subtrees. So this, okay, I try to do the exact same thing. Now if A is equal to null, I do this, and this is the same thing. Okay, now I will have a global answer variable, which will be initially, let us say, int min. And I will say that answer is equal to max of answer, comma, what I got from here. I mean, like, that is a triangular path, right? That is a triangular path. But now I can't return this path. For example, suppose there was a 2 here. There was a, let us say, a 7 here. Okay, this 7 needs to know a very straight path that will be ending at 7. So it can't include a path that will be 3 to 1 minus 4 minus 5. It should be one straight direction path, right? So I will return the A plus max of these two, max of left path, comma, right path. Okay, because now I need only a one direction path. I don't need a cross and a straight line path, right? That is wrong. So answer is equal to int min. So I will always have to set it in when I start the function. So answer will be int min. That makes some sense. Then I will compute the left path, I will compute the right path, and I return this. Great. So I will just do a what we say, max path ending here of A, and then I can finally do return answer. That should be correct. That should be correct. Earlier I was passing this thing completely there, which is totally wrong. Answer is equal to max of answer eval plus what is the issue here? Okay, I missed a semicolon. Did I miss anything else? No, seems fine. Return a val plus this. This is quite fine. I think this was the answer that was supposed to be written. I'm not really sure, but this seemed to be one. Yes. Yep. So I hope you guys were able to understand that what my function was returning was a path that could be like this and then something here. So this was a triangular path, which is not correct. So then it will cause an issue up on the upper side. Okay. So then I try to let me submit it and it should be working. Okay. We got 389 out of 400 points. Interesting. Let's briefly watch the n log n solution of the longest increasing subsequence and then we will end the lecture. Okay. Acha. Now suppose you are creating a subsequence. Okay. Now let us say my subsequence is like this. I mean, like, I'm not going to explain that solution in a lot of depth because we can discuss it in the section that we will be discussing. I mean, like, we can have a separate video on discussing this as well. In fact, that will be a very good thing. We can upload a video there to the channel. But I mean, like, I will still try to give a kind of an intuition to this. Okay. Suppose we get, I mean, like, we are trying to create a longest increasing subsequence. Okay. When we get a zero, our initial subsequence will be only zero, right? This will be the initial subsequence. Okay. Now, when we get a 8, where would you like to put this 8? You would, I mean, like, it makes total sense to put this 8 here. Correct? Okay. Then we get a 4. Now, we try to see where can we put this 4. This 4 should, I mean, like, replace a particular number, right? This 4 should replace a previous number. This 4, I mean, like, by the way, do you guys, I mean, like, guys, try to see that this particular array that we are creating is sorted, is always sorted. Okay. Now we try to see which 4, I mean, like, which 4 can go where. Out of these two, 0, 8, 0, 4, which is a better thing to take? 0, 4 is always a better thing to take, right? Because 0, 4 can later be expanded to 0, 4, 7 of size 3, but 0, 8 won't be able to. So 0, 4 allows us more scope to expand it, right? So what we do is we try to find the first number in the current increasing subsequence that is greater than 4. Okay, so we find this 8, we replace this 8 by 4. And what is the length of the current subsequence? It is still 2, right? What is the length of the current largest subsequence? It is still 2. Great. Then we go to 12. We try to find the first index that is greater than 12. There is no index. So that means we put 12 here. Now what is the length of the largest subsequence? It is 3. So basically try to see that the array that we are maintaining is storing the length of the largest subsequence. That will be our answer. Now we go to 2. We try to find the first index that is larger than 2. We find this is 4. We replace this 4 with 2. What is the length of the largest increasing subsequence till now? It is still 3. And by the way, if you would have seen till here, the length of the largest subsequence is 3, right? Great. Now we try to put 10. We put 10. We find this is the best place. We replace this by 10. And what is the length of the largest subsequence till now? It is still 10. And also, if you would have seen, the length of the largest subsequence till this place is also 3, right? Okay, now we go to 6. We replace this 10 by 6. Now we go to 14. There is no number that is greater than 14, so we put 14 here. And what will be the length of the largest subsequence now? It is 4. And you also see that the length of the largest subsequence is 4 here. Okay, now let me try to write the code, and then the other things will start becoming more clear to you. Okay, so let me comment out this code. This was the DP code. And let me write the binary search code now. Initially, my current array will be empty. Okay, then I will say for I equals to 0, I less than n plus plus I. First thing I will check if array I, if if current array dot empty or array I is greater than what we say current array dot back. If any of those two cases is true, in what does that mean? If these two cases is true, that means I will push the current number, right? Because here 14 was larger than whatever was here, that means 6. So I just pushed back 14. I increased the size of my current array with 1. Okay. Then what is the other case? In the next case, I will try to find first index that is greater than or equal to the value greater than equal to AI. Okay. How can I do that? As the current array is always being maintained in a sorted order. I mean, like if you would have observed this above thing, this would have always been maintained in a sorted order. I can binary search this. I can say L is equal to 0, R equal to 0. Then I say while L is less than equal to R, mid is equal to L plus R minus L by 2. If array mid is greater than equal to array I will say index is equal to mid, R is equal to mid minus 1. This is normal binary search. Okay. Else L is equal to mid plus 1. I'm basically trying to find the first index that has the value greater than or equal to mid. Okay. So I will say int is equal to minus 1. And what I do after this, I just change my current array int to array I. Okay. What should R be? R should actually be equal to current array dot size minus 1. Awesome. And finally, I can just return my current array dot size, because that was always storing the length of the largest increasing subsequence till now. Let us try to test it. Yep, and this is correct, and this is submit. Now what did I do? Shit. Okay. Again, I am failing at this case. Oh, I have a runtime error. Why do I have a runtime error? I say current array dot empty or array I is greater than current array dot back. That is fine. Am I anytime in? Yes. Okay. I have to find the very first index that is greater than or equal to the current number. Okay. Can the index be -1? Can it happen that all the numbers are greater than or equal to the current number? In that case, I will just return 0, right? In that case, I will just return. Okay, when can index be -1? This can be -1 if all the numbers in the array are smaller than. So yes, if all the numbers are smaller than that. So I can say if index is equal to -1, that means all the numbers in the array are smaller than that number. Then this will be happening, right? If index is equal to -1, when can that happen? That can happen only if all the numbers are smaller than that. All the numbers are smaller than that, because if there was any one index that was greater than or equal to AI, then I would have changed my index to that mid, right? And I'm saying that all the numbers, all the indexes are smaller than that. Else if array mid is greater than equal to array, sorry, we have to actually check else if current array mid. Okay, so this is the issue. It should be current array mid. Let us test it. So we just had a naming issue. And if we were checking array mid, we should have checked current array mid. This, I mean, like, this is running wrong. That is another issue. I say that okay, and I can then set the current array mid is greater than equal to AI index is equal to mid. If current array mid is greater than equal to AI, then that might or might not be the first index. Then I try to reduce it. Okay, current array dot pushback is correct. My current array is the array L is equal to 0, R is equal to current array dot size -1. That is perfectly fine. I say while L is less than equal to R, I try to find mid. I try to see what is the number at that mid index. Is it greater than or equal to the current number that I'm going to add? If it is greater than, for example, suppose I was going to add 15 here, I go to 6. Is 6 greater than or equal to 15? No, it is not. So I will have to search here. Is 14 greater than equal to? Yes. 14 is also not, so I will go here. So let us say that we were trying to add a number 3. Let us say we were trying to add a number 3. I try to see here. I'm like, is 6 greater than equal to 3? Yes, it is. So it can be the answer, or the answer can be somewhere here. Correct. So, and I'm returning the current array dot size. That makes some sense. That makes the sense. But why is the answer 14 in? Why is the answer 4 in this case? The answer should be something like 14. So I try to find the first index, then index is equal to mid. If index is equal to, this should not be happening. Oh, this is correct. Yep, you're correct. Because I had added that if condition while debugging, I forgot to remove that. That was the issue. Correct. We got all the points correct. I think many people don't know that this problem can also be solved in n log n in this small code only. Okay, so in this small code, so that was a new thing.
So today's session is on the dynamic programming day 2. So here I have the questions, and the questions demand that has been made is of buy and sell stock 2. So let's dive into that question. Okay, let's get started. Say you have an array A for which the ith element is the price of a given stock on day I. Okay, you have to design an algorithm to find the maximum profit. Now you may complete as many transactions as you like. That is, buy one and sell one share of a stock multiple times. However, you may not engage in multiple transactions at the same time. That is, you must sell the stock before you buy again. Okay. So let's actually see the example and let's see what it means. So we have an integer array which represents the day wise stocks that are available. Now the output is 2. That means, so here it says that we have bought the stock on day 0, that means 1, and we have sold it on day 1. Okay, first of all, let me name them. So let's utilize this space. Let's say we have so this is index 0, 1, 2, and index 0 we have 1, 2, 3. So we bought the stock on day 1, on day 0, and we sell it on day 1. So we get the profit of 1, right? And if we buy it on day 1 and sell it on day 2, so that will be again a profit of 1. So that means total profit is equal to 2. So that is what this example is saying. And if we look at the next example, so we can buy the stock on day, so it says that buy the stock on day 1, that is cost is 2, and sell the stock on day 2, that is at this, right? So that means the profit is 10 minus 2, and that is 8. Now the thing it says is that we can buy and sell multiple stocks, but the constraint is that we cannot keep on buying the stock and keep storing it with us and with the intent of selling it later. We cannot do that. So please understand this problem. Many people feel confused with the problem. So it says that once you have bought the stock, first you have to sell it, and then only you can again buy it and then sell it, right? So that's what the problem is. So let's say we have 7, 1, 5, 3, 6, and 4. Okay, these are the prices of the stocks on days. So 0, 1, 2, 3, 4, 5 are the days. Now let's talk about the brute force solution first. Okay, now the brute force solution would be that I can buy the stock, right? So I can buy the stock here, and then I can see that when can I sell the stock. Okay, so if I buy the stock at first at 0th day, then can I sell the stock at any day? No, right? Because this stock is greater than, has a greater value than any of the stock, right? So therefore I cannot simply sell this stock. Let's move to the next element. Now on the next element, if we buy the stock, then we can sell it on day 2, we can sell it on day 3, on day 4, day 5, right? So now the possibility is that let's say I sell the stock on day 2, so that will give me a profit of 4, and plus now there is a sub problem, isn't it? So I will add the cost to the sub problem, and the sub problem is of 5, 3, 6, 4, isn't it? Now this is the sub problem that I can try buying this stock and sell it on the further days. So just what I have discussed now will be applicable to all the sub problems. Okay, so this is the case when I have sold my stock of 1 on day 2, that is at the cost of 5, that will give me a profit of 4. Now if let's say I sell the stock on day 3, so that will give me the profit of 2, and I have a sub problem which is 3, 6, 4, right? Likewise, if I sell the stock on day 6, so that will be a profit of 5, and that will be giving me the sub problem of 6 and 4, right? And if I sell the stock on day 5, so the profit is of 3, and I will get the sub problem of 4, right? So this is it. Now this will happen with every element. Okay, so as I move to 5, this will happen with 5 as well, that I can, so first of all, when can I sell this stock of 5? So I can sell it on day 4, right? So that will give me a profit of 1, and the sub problem is of 6 and 4. So for 5, that's it, right? Then we will move on to the next element, and 3 can be sold on day 4, so that means give me a profit of 3 plus 6 comma 4, and I can sell it on day 5, so profit is of 1, and the sub problem is this, right? So likewise I can keep on going on, and that will give me these sub problems for every element. Okay, now the thing is that there are n elements, and if you see from this visualization that I have created in here, so if you see on the first level, we are, for n elements, we are having n iterations, we are having n possible cases. So that will give the time complexity of order of n square, right? Yes, so Goyal TY, yes, you can. So if you are buying a stock on first day, and if you are selling the stock on the second day, then you can immediately buy the next stock on the second day. Okay, so if you see from the problem that has been given on the platform, then you'll be clear. Okay, cool. So now for n elements at the first level, we are having n possibilities. So the time complexity is of n square. Now this is happening n times, isn't it? For every element, this could happen n times in the worst case. So that is the first level, right? And now such that I'll be having the next level having n elements, n possibilities for n elements, right? Then again at the next level I'll be having n elements and so on. So that will be like n into n into n and so on. So it will be n to the power n. The time complexity is of n to the power n, which is very huge, okay? Which is very huge. So now let's see how can we optimize this using DP. So this was the brute force approach. Now let's see. So we have 7, 1, 5, 3, 6, 4. Okay, let's say this is my DP array, and here this I'm going to do in bottom up fashion. Okay, I have a 1D array. Now if let's say I have only a single stock, then is there any point of so there won't be any profit, right? Will there be any profit? No, right? Can we make it 0? So here we can put the value 0. Okay, we can put the value 0. Now, so basically at DPI, I will say that it will be nothing but maximum profit we got by doing transactions only till that ith position. Okay, so if let's say I am here, then this is the, let's say, the last point where I will be calculating the profit for, and that I'll be doing for every element. Okay, cool. Now I am at this index, I am at this position. Now the thing is that either, so basically we are actually taking it in a way that what profit can I achieve on this ith day. Okay, so I can either sell a stock or I don't sell a stock. If I don't sell a stock, that means whatever is present over here will be my answer. Okay. But if I sell a stock, then I'll be actually moving from the first location till the I minus 1th location to check if there is a value which is lesser than this value on which I can. So let's say I am at index this. Okay. Now for this index, let's say this is I and J is at this position. So basically either I do not sell any stock on this day, or let's say I sell a stock this on this day. Why am I able to sell stock J on this day? Because J is lesser than I, right? Element at J is lesser than I. So that I have to keep on checking. So there are two possibilities now, that I can sell a stock on one day, on that particular day, or I cannot sell a stock on that day, right? So here what we'll get, so the idea is that for I which goes from 1 to n minus 1, okay, and let's say this is our DP array, and DP0 will be initialized to 0. Now we'll be doing for J which goes from 0 to I minus 1, okay, what we'll be doing. So also what we have to take, so we have to take that when we are not considering the element, so in that case whatever is the answer at DPI minus 1, we will have that. Okay, we will have that. Now this is the case when I am not selling the stock on that particular day. Now when I have to sell, so I'll be moving through this loop. What I'll be doing is DP of I will be equal to maximum of DP of I, okay, comma deep AI, that is the so wait a minute, it will be whatever the profit is at DP of J plus A of I minus A of J. So this is the additional profit that I have got while selling the stock on day I, that I have bought on day J. So this is the profit, and this will be added to whatever was the profit on DP of J. Is that clear? Is this thing clear? that whatever was the profit on jth day, that will be added to the profit that I have achieved now. Okay, so this is what the idea is, and this we'll do for all the elements. Cool. And the time complexity would be order of n square, right? We have two loops. So from order of n to the power n, we have actually come to order of n square. Are you guys able to relate that why it's order of n square now? How are we processing through this? How are we moving through this? Is it fine, guys? Cool. So let's code it quickly and then we'll move on to the more optimized solution. Okay. So let's quickly code it. So we are taking an array, right? So int dp, first of all, let's consider the size as well. Okay, so here I have int 10 where I'll take the size. Then if n is equal to 0, or if n equal to 1, then we'll return 0. Okay, cool. Now let's move ahead. Let's create our dp array, and let's initialize all the elements to 0. So dp of I is equal to 0. Now moving forward, so we are going to all the elements starting from index 1. Okay, so starting from index 1, we go to all the elements, and what we'll do, we'll put the dp of I is equal to dp of I minus 1. That is when we are not selling the stock on day I. Okay, but when we are selling, so we have to check that when that stock was bought. Okay, we will go from 0 all the way when j is less than I and j plus plus. Now, so it will be nothing but dp of I is equal to maximum of dp of I comma dp of j plus a of I minus a of j. Okay, and then we'll simply return dp of n minus 1. Let's see if this works. Cool, it worked. Okay, so we have actually got the partial points. Now this can be further optimized. Okay, let's see the optimized case now. So here, let's move forward. Now this can be further optimized if we make some observation. Okay, so what I'm doing over here, I am actually, whatever was the profit on day j, I am adding it to my current profit, right? Okay, so here we have this solution. Cool. Now dp of j plus dp of I minus ai minus aj we have. Now if I tweak this a little, so what will I get? I will get ai plus dp of j minus aj. Can I write it like this? Can I write it like this? Okay. So now so basically we have to increase our profit. Okay, to increase the profit, I want this to be increased, and for that I want this to be increased, right? So to increase this, that is the difference shall be increased. Okay, so for that we can maintain. So we were just iterating through the j loop to get this difference, so that this could be maximized. We were checking for which j value is this difference maximum. Now instead of iterating through that j array, we can actually keep on storing the maximum value of this till now. Okay, till now. Does that make sense? We were only moving our j loop for checking that for which value of j are we getting this, are we getting this as the maximum, so that our the complete value is maximum, right? So instead of going to each jth position, we can actually store this particular value in a variable, and then we can keep on updating that variable. Yes, the greedy method is of order of n time complexity, and we'll also see that how this can be changed to order of n time complexity. Okay, Ankit, does that make sense? So let me just code this thing now, or let me just code it. If you guys still have any issue, we can discuss it. Okay, so let's just proceed now. So here basically we have to change, we have to remove this loop. Okay, so for that basically we have to keep on storing this particular value, as in we have dp of j plus, we have this here. Now I am changing it a little to get a of I plus dp of j minus a of j. Now I am trying to store this value. So here I can maintain a maxi variable, let's say, which is initially is equal to 0 minus a of I, a of 0. Okay. So basically this will be gone. This will be gone. And we have maxi is equal to, sorry, first we have to update the dp of I. So dp of I is equal to max of dp of I comma a of I plus plus maxi, right? So basically here this value has been replaced by maxi. Okay, and also we have to update our maxi variable, max equal to maxi comma dp of I minus a of I. Okay, and here we go. So now we will simply, so here we have actually eliminated the jth loop. Does that make sense to everyone? Now let's see if this works. Let's see it, and here we go. Cool, we have actually got the solution correct. We have got all the points. So now this is the solution of order of time complexity is equal is so time is order of n square, right? Sorry, order of n, and space is order of n only, right? Order of n. But the space can also be optimized in this case. The space can be optimized. If you carefully notice over here, then we have, so basically dp of I is equal to dp of I minus 1. For every ith position, we are actually, we are reliable on this dp array because we want dp of I minus 1. So if we store somewhere this dp of I minus 1, and if we utilize it in some way, so then we can, actually do it in just order of one space. Now I want you guys to try that thing. So here we are at time of order of n and space of order of n. So let's move on to the next question, and the next question is minimum jumps array. So this is a very important question. So given a array of non-negative integers a of length n, you are initially positioned at the first index of the array. Each element in the array represents your maximum jump length at that position. Return the minimum number of jumps required to reach the last index. If it's not possible to reach the last index, then return -1. Okay. So the first and the only argument that we have here is of integer a. Now let's see what the problem says with the help of an example. So we have 2, 1, 1, and the array is 2, 1, 1. So the output is 1. Why? Because the problem says that from index 0, we have to reach the last index. So we can take simply the jump of 2 to reach the last index. So the element at that position signifies that how many jumps we can take at max. Okay, we can take the jump of 1, we can take the jump of 2 for this particular variable. Here we can take just the jump of 1. Again, we can take the just the jump of 1. So let's say I have 2, 1, 2, 3, 1, 1, 4. Okay. Now let's maintain the DP. So here we are going to do the DP thing. So this is the bottom of DP that I have taken. So basically, if I talk about the brute force approach in this case, then what we'll do, we will check till all the, so whenever I am at some position, I can go to, from here, this is 2, so I can go jump to here, or I can jump to here, right? Then I will again call for this part as well as this part, okay, till the position that I can jump for the first element. Then after jumping to, let's say, 3, I will call for rest of the sub problem, and after jumping to 1, then I will call for rest of the sub problem. So this will go on for every element, right? So this is the brute force solution. Now let's talk about the DP solution. For DP solution, we have created the DP array. Let's name it 0, 1, 2, 3, 4. Okay, so basically the DPI signifies that till that particular position, how many minimum number of jumps we can take. Okay, so DP of I tells the minimum jumps we can take from 0 to I. Okay, so if we are standing at this position, then we don't have to take, so considering this position as the last index, we don't have to take any jump, so this will be 0, right? Now if I am at index 1, then from index, so so to calculate the number of jumps to reach index 1, that means, so let's name it here 1, 0, 1, 2, 3, 4. Okay, if I want to go to index 1, then I have to start from 0 till I minus 1. Okay, I will check that from index, so let's start J from here. I will check that if from this position I can go to this position or not. How to check that? We will do it in way like 0 plus, that is the index J, plus A of J. If it's greater than equal to I, that means we can move from index J till index I. So this is 0 plus 2, that is 2. It's greater than equal to 1. Here 1 is I. So we can move from this element to this element, and we will get what? We will get nothing but the cost, the jumps we need to reach at this position plus 1. Does that make sense? Now we come, we are done with these positions. Now we go we place our I at here, and J will again be placed at 0. Okay, so from 0, can we move to this? So this is nothing but 0 plus 2, and that is 2. 2 is greater than equal to 2. We are at index 2 now. So yes, so that means there will be nothing but 0 plus 1. So 1 will come over here. Now our J will move to this position. Let's see if we can from J till I. So this is nothing but 1 plus 3, that is 4. It's greater than equal to 2. So yes, we can jump from this position, that is from this position to this position, and that will be nothing but whatever is present at this position plus 1. So we have to check that if dp of I is equal to max of dp of I, comma dp of j plus 1. So right now dp of I is maximum, then dp of j plus 1. So it will remain 1. Okay, and this we will go on till the loop is completed. Okay, let's first code it up, then we will complete the array. So we have, so we'll take the size of the array, and if the size of the array is equal to 1, that means only one element. So we'll return 0. If the size is equal to 0, but if the first element is equal to 0, in that case we will return 0, right? We will return 0. Sorry, if n equal to 1, we will return minus 1, because if we cannot take, if we cannot reach to the end element, okay, sorry, this will be minus 1. That means we cannot go, right? Now let's move on. Let's dp is equal to dp of n. Now dp of 0 be 0. So for int I equal to 0, so sorry, we'll start with 1. I less than n, I plus plus, and dp of I shall be initialized to int max. Cool. Now what we have to do, we have to run our second for loop, that is int j is equal to 0 till j is less than I and j plus plus. Then if, okay, so dp of I is equal to maximum of dp of I, comma comma, we have dp of j plus 1. Okay, and we will at the end return. So if the last element was reachable, that means if dp of n minus 1 is equal to int max, right? So that means it was not reachable. In that case, we will return minus 1, else we will return dp of n minus 1. Okay, where did it fail? Okay, so we actually didn't check the condition here. The condition needs to be checked that if a of I, if j plus a of j is greater than equal to I, and also we have to check that if dp of j is not equal to int max. Why? Because it's a possibility that we could not reach dp of j, right? So in that case, but if we can, so we will calculate, right? Now let's see. Okay, sorry, this should be minimum, right? Okay, we actually have got the partially correct solution because the thing is that this is also possible. This the solution to this problem is also possible in order of n. That is the greedy approach. I want you guys to explore that approach. Okay, here we have discussed the different solutions. So if anyone has any doubt, you can ask in this particular solution. So Alind, we are adding aj to j because we are checking that if from jth position, if we are able to go to I or not. Okay. Why are we doing j plus a of j? Because we are checking that if from some position, will we be able to go or not? Okay. So if we are at this position and we are trying to jump to this location, we won't be able to go because we can only take at most 2 steps. So that's why we are checking j plus, that is, this is 0. So 0 plus 2, that is 2. It's lesser than the index I. Let's say I is here, and therefore we cannot jump till here, and therefore we are checking the condition. Okay, is that clear? Sure, let's move to the next problem. And next problem we are taking is of edit distance. Okay, the problem is, first of all, it's very important. So the problem is important because it is asked in many interviews. Okay, it's very common, and you should definitely understand it, like how it works. So let's dive in the problem. So it says that given two strings a and b, find the minimum number of steps required to convert a to b. Okay, each operation is counted as one step. Now you have the following three operations per word, permitted on a word. The first is, it says that insert a character, okay, delete a character, and replace a character. So to convert a string A to B, I can do these three things, okay, and I have to find the minimum steps that I can take to convert one string to another string. For example, in the input, let's say we have ABAD, and we want to convert it to ABAC. So here we can simply replace D by C, right? And that will give the cost of what? 1, right? Now here in this case, it says that the cost is 2. Why? Because here we are replacing S with T, that adds to the cost of 1. Then here we are actually inserting, so after converting this S to T, we will be inserting I. Okay, so that will add up another 1, and the cost will be 2. Okay, so is the problem clear to everyone? So basically we have to convert a given two strings are there, right? So we have to convert string A to string B. We can make 3 possible conversions with each character, that we can replace a character, we can insert a character, and we can delete a character. Okay, so we have to do it in minimum possible time, minimum possible steps. So let's see. So let's say I have Sunday over here and I want to convert it to Saturday. Cool. So what can we do here? Day at the end are same. So now we can actually convert this sun to Saturday. And what we can do? We can, so this is also same, right? So that means we are left with UN and ATUR. So we can insert insert what? So guys, here we are going to do it using 2D DP, the bottom up approach. Okay. Here I have actually, so we are trying to convert this string to this string. Okay. Let's see how we'll proceed. Here we are going to convert this string to this string. We have to consider the empty cases as well. When let's say this string is empty, so this is that case, and let's say this string is empty, so this is that case. Now, if we want, so this is what we have to convert in. So let's say if we want to convert this to this, what we'll have to do? What should be the output here? It shall be 0, right? I don't have to do any operation. Now, if I want to convert this empty string to S, in that case I have to add one character. If I want to convert this empty string to S and A, for that I have to add 2 characters, then 3 characters, 4 characters, 5 characters, 6 characters, 7 characters, and 8 characters, right? So that's what I have to do. Now what if we have to convert this string to just an empty string? In that case we have to delete one character, then we have to delete 2 characters, right? To convert Sunday to empty string, we have to delete 3 characters. To convert sun, we have to delete 3 characters. To convert SUND to empty string, we have to delete 4 characters, then 5 characters, and finally 6 characters. Okay, so this is the base case. This is the base case. Now, the point is that whenever, so at some, if we are standing at some position, right? Let's say we are standing at some position, then we are actually trying to do what? We are trying to see if I want to get the answer till that particular position. That means I want to get the answer for this and this, right? Answer for this and this part. Then what should I do? So please note that this is, let's say, the box and we are standing at here. Okay. Now this is the case. So this is the case when I'll be ignoring the current characters. Okay. When can I ignore the current characters? When the character at this place and this place are same, then we can ignore them and we can take whatever the value was previous, right? Whatever the value we had, so we can take this value. We can take this value. Okay. We can ignore and we can, so let's say I have, so this and this are same, right? This and this are same and the corresponding block is this. So we can ignore this and whatever is the result from till here and here, we can consider that. Okay, we can consider that. So I hope it makes sense that why are we taking this position if there is a match? I minus 1, j minus 1 when there is a match. Okay, now this is the case. So just the position above the current cell, this is the place when we can insert an element. Okay, so this is for inserting an element. So when we have not found a match and we want to insert an element, so we will pick up the, so that means let's say here we are, okay, and we want to insert an element. So we will be checking this particular location. Okay, we will be checking I minus 1 jth position. So here we have I minus 1 and j, and then for deletion we will be checking I comma j minus 1. Okay, why? Because if let's say, so let's say we are at this block only and or let's say when there is not a match, let's say this block. Now this is deletion. Why? This signifies deletion, that when we are not considering this, so when we are just considering, so we are ignoring this character, and that means we are just checking what was the result for this and this string. Okay, so then at that point we can take this value. Okay, makes sense that we are ignoring this character, we are deleting this character, and we are checking that what was the maximum when we have ignored this character. Okay, because if we are ignoring, that means we don't have to check for this particular position. Whatever will be the value ignoring this character, we will take it from its left cell. Okay, now let's proceed with our let's proceed with this. Let's see what we'll get. Let's try run the approach. Cool. So here S and S match. Therefore, we can ignore them and take whatever is present over here, that is 0. That means we have to make no changes and therefore the steps are 0. Now we go to this S and so we go to this S and U. They don't match. Whatever is minimum at this location or this location or this location, we will take it and we will add 1 to the cost, because now we are considering these elements as well. Okay, so 0 is minimum, we will take 0 and add 1 for the current operation. Now let's move on. So we have, now we will be checking for, so let me fill it. So S and U, so we are at S and N, they don't match. We will take the minimum of this and this. So 1 is minimum, this becomes 2. Now S and D, so S and D also don't match. The minimum is 2, this becomes 3. Now S and A don't match, minimum is 3, this becomes 4. S and Y don't match, minimum is 4 and this becomes 5. Now we are at this element and we will check again. So A and S doesn't match, minimum is 0, we will take 1. Then A and U don't match, so 0 is minimum, we will add 1 to it. A and N doesn't match, 2 we'll get. A and D, for A and D what we'll get? We will get 3. Then here we will this match, right? So we will take this cell, so add 1 to it. Sorry, we don't have to do anything, we will just take it. Okay, we don't have to add to it. Cool. Now A and Y are there, so 4 will come over here. Then so likewise, shall I fill the complete table or it makes sense now? Is it clear that we have to take the minimum of the 3 cells, that is the above, the on the top left corner, on the or the, so either, so if you are standing at this, so minimum of this or this or this. Okay, so let's code it. And finally we'll get our result at this location. Okay, because ultimately we are considering the complete string. The single cell actually tells that what is the value, the jumps till that particular position. Okay, the last cell will tell us the final result, so we will return the last cell. So we have the, let's take the string length in some variables. So let's say m is equal to a dot length and n is equal to a dot b dot length. We will take a 2D DP where it will be of a size of m cross n, right? And the first cell will have a value of 0, right? Because that will signify the empty strings. So to convert an empty string to empty string will cost us 0. Now what do we have to do? So basically we have to do the base cases thing, right? So I is equal to 1, we will start from 1, I less than, so rows is m, right? And okay, so string a is equal to, so we have string int I equal to 1, I is less than equal to, okay, so here the string length n, we will be going through all the, let's say all the columns, so that is n. Okay, and I plus plus, so that will be dp of 0 I is equal to dp of 0 I minus 1 plus 1. What are we doing? We are actually initializing our base cases. Okay, we are just adding the values from the previous cell on the top rows and the top, on the top row and the top column. Int j is equal to, let's say 1, and j is less than equal to m, j plus plus. Now dp of, so dp of j 0 is equal to dp of j minus 1 0 plus 1. Okay, cool. Now let's move through all the cells, that is it's equal to m and I plus plus, then for int j equal to 1, then j less than equal to n, j plus plus, then int, let's say we are taking the, storing the distance like this, so q1 denotes the cost, c1, let's say cost is equal to dp of I minus 1 j. Okay, so this is the cost when we are inserting an element. Int c2 equal to dp of I j minus 1. This is the cost when we are deleting the elements, and this is the cost of replacing the element. Okay, I minus 1 j minus 1. By replacement, it means that we have changed the character to the character that we want. Now if the current character, if it's same, right, I minus 1 is equal to b of j minus 1. So at this point, dp of ij is equal to dp of I minus 1 j minus 1, right? We don't have to add any cost because the characters are same. Else, what do we have to store? So we have to store dp of ij is equal to 1 plus minimum of q1 comma minimum of q2 comma q3. Okay, and finally we will return dp of mn. Oh, these are not q1 q2, these are c1 c2 c3. Cool. Okay, dp of int m is equal to a dot length, perfect, mn dp of m plus 1, right? Sorry, so it should be m plus 1. Okay, let's see now. Cool, we have got the solution. Cool. So let me actually make you go through the question that we discussed previously. I think few of you had doubt in that. See, we are doing DP and we were doing it in bottom up manner. Okay. Notice that what DP, so you should know that what the state of the DP is, right? What these cells represent, and that actually tells what's the state of the DP. So this is the DP array and this is the given array. Now the state of the DP says that DP of I is equal to maximum profit by doing, we have got by doing the transaction till that particular point. Okay, if we are standing at here, then from 0 till this point, what is the profit that we have achieved? So that's what the DP of I tells. Is that clear? Now moving ahead, at position 0, we cannot sell this stock even if we buy. So therefore the profit is 0. Now if we go to the next position, so here we have to check for, we have two options. Either we can take this up, we can sell the stock on this particular day to get the profit. So that is one, sell the stock. Second is don't sell, right? So these are the only two options. Now in case of sell the stock, we will start. So let's say we are at position this, and for selling the stock, we will start from this position all the way till this position. Okay, till I minus 1, this is I, till I minus 1 we will go. We will check if the value of jth element is smaller than this element, right? And also what we'll check that whatever is the value at, let's say j is here, actually let's say j is here. Okay, now whatever is the value till this point, we will add to the profit we have achieved by selling stock 1 on by selling the cost of 1 on for cost of 3. That means dp of j plus a of I minus a of j. Make sense? Does that make sense that why is this condition for? Now this is why we have taken this thing. Okay, so this is the case when we are selling the stock. We will check for every I, we will check for every j, starting the j from 0 all the way till I minus 1. We will check for this condition. And there is some other case as well when we don't sell the stock. if we don't sell the stock, then we take whatever is present on its previous day. So let's say we want to see the cost of this. So if we are not selling on this day, then we are actually checking whatever is present on here will come over here. Okay, so whatever is maximum from whatever is maximum between this, that is when we are selling the stock and when we don't want to sell it stock, so whatever is maximum, we will take that value in here. Does that make sense? So that's essentially what we are doing. Okay, so that's what the DP solution is of order of n square. Okay, the pseudocode says that we'll take the DP array, then DP of 0 will be initialized to 0 because of the condition I told over here, that we can, if we even buy it, we cannot sell it, and we will go to all the elements starting from position 1 all the way till n minus 1, and if DP of I is equal, so here we are actually taking the previous DPI. That means we are actually not, this is the case when we are not considering selling the stock on day ith. So therefore we are taking the cost till I minus 1. We are taking the profit till I minus 1 day. I hope that makes sense. Now moving ahead, if we want to sell it, so we are going from j, we are going j equal to I minus 1, right? And we will be taking whatever is maximum between DP of I minus 1 and this condition that I told you. Okay, so this is the condition when we are taking stock, when we are selling stock, and this is the condition when we are not selling. Okay, now this will do for all the elements, and that will take the time complexity of order of n square. Now I said that we can optimize it. So if we see this particular condition, right, in this condition we want to maximize this condition. I have actually changed it to this. Okay, I have changed it, and this I have got now. So to maximize this should be maximum, right? Now we are actually iterating in this j loop to find that for which value of j this is maximum. Okay, so instead of going through every element and checking for which value of j this thing is maximum, we can actually keep on storing it from the start. Okay, so that's what we are doing over here, that we are storing it from the start. We can actually maintain a max variable. Let's call it max var. Okay, and this can, so initially it will be initialized to DP of j, which will be nothing but 0. Initially the DP of j is 0, right? And we will be doing 0 minus a of j. Okay, minus a of j. So we will get DP of 0 minus a of, let's call it variable only. Okay, let's call it variable, equal to a of 0. Okay, this will be initialized. Now whenever we'll be moving in a loop, right? So let me write it. So for I DP array DP of 0 initialized to 0, variable, let's call it maxi only. Okay, now it will be initialized to DP of 0 minus a of 0. Okay, so for I which goes from 1 to n minus 1, DP of I is equal to DP of I minus 1 when we are not selling the stock. So we are taking the stock of the previous day. Now if we are selling the stock, so we will do DP of I equal to maximum of DP of I, comma, what we want, a of I plus maxi, and then we will update this maxi variable to max of maxi, comma, DP of I minus a of I. So essentially we have done it in just order of n.
So today is the third and the final day where we will be solving particularly DP problems. So we will start with the road cutting problem, and if there is any other request for a problem that you want us to solve, please do mention in the comments, or I will pick up any two randomly. Okay, great. Let us begin. The problem says that there is a road of length n, okay, on x-axis. So basically it's an horizontal road with its left end at x is equal to 0 and right end at x is equal to n. Okay, so basically n plus 1 points are there. Now there are m weak points out of those n plus 1 points, denoted by positive integer values all less than n. So basically there are m a1 to am weak points. Okay, we have to cut the road at all these weak points. Okay, so we have to make a cut at these points such that you can perform these cuts in any order. After a cut, road gets divided into two smaller subroads. Yeah, because it will be divided. Okay, cost of making a cut is the length of the subroad in which you are making a cut. Cost of making a cut is the length of the subroad in which you are making a cut. Okay, your aim is to minimize this cost. Okay, return an array denoting the sequence in which you will make cuts. If two different sequences of cuts give the same cost, return the lexicographically smallest. Okay. Okay. Basically, we have to give the sequence of points in which we will cut, right? And the points should be lexicographically smallest. And we have to basically we have to denote the sequence as well. Okay, that what will be the sequence in which we will cut. So basically, there is a road 1, comma 2, comma 5. So that means I will first make a cut at. So this is the I have to minimize the cost. So minimum cost will be here in those two. And out of these, the minimum will be 2, comma 1, comma 5. So I have to return 2, comma 1, comma 5. Got it. Okay. So I mean, like the problem to find the minimum seems to be a simple DP problem that hey, I mean, like DPIJ can represent the minimum cost to what we say to cut from index I to index j. That can be a possible thing, but let me say that what is the value of this n? Okay, the n can be up to 10 to the power 9. So basically, we can't create a 10 to the power 9 DP table anyways. So we have to do something in terms of m. So if I have made a cut here, then let me think of the DP table. I mean, like in any DP question, when it comes, I try to first find that what the state relation can be. And I haven't seen this question earlier, so let me think what the status, what the DP state can be. So for example, n is equal to 6 and a is equal to 1, comma 2, comma 5. Okay. Let me, I mean, like when the values are not given, is m always less than n or less than n? Okay. By positive integer. So a1 will be greater than 0 and am will be less than n. So let me say I add 0 here and I add 6 here because padding often helps in such DB problems. And then if I create a 2D DP, I'm not really sure if I should create a 2D DP, but if I create a 2D DP, then it should be, then the answer should be, let us say that the indexes are uh, 0, 1, 2, 3, 4. So my final answer should be in DP 0 to 4. Okay. Which will represent the minimum sum of costs to split roads, right? Okay, let us say that we say this. So Abhishek has asked to please explain the question. Sure, Abhishek, let me explain the question again. So basically, we are given a road of length n. On these road, there are some points. There are m points like a1 to am, where we have to make cuts on the road. Okay, the cost for a cut is equal to the present length of that particular road. For example, suppose there is initially the road of length 6. Suppose you make the cut 2. Suppose you first make the cut at position 2 or position 1 or position 5. The cost that will be added will be 6 because that is the current length of the code. Now, suppose you had earlier made the cut at 2. Now, when you will make the cut at 1, the length will be 0 to 2, right? The length will be 0 to 2, which will be 3. So the cost added will be 3. So that is, I mean, like then you have to find the minimum permutation of cuts such that the total cost is minimum. So suppose that is the minimum cost or minimum sum of cost to split roads from index I to index j. Okay. Then that means I can make cuts from index what we say I plus 1 to j minus 1. Let us say that we say this. I mean, like I can make cuts from index I plus 1 to j minus 1. Let us say I can make cuts. Suppose that particular index is k. Okay, suppose that particular index is k. Then after this, the problem will reduce to dp of I to k, because I have already made a cut at k, plus dp of k to j, plus what is the current length of that, right? So, okay, I mean, like, I can say the minimum sum of cost to split roads such that, then I think I should change that, such that the current road is of length I to j, is of length I to j. I mean, like j minus I plus 1. Or what we say, ai to aj. This seems to make some sense. Okay, then I will add what is the current length of the code of the road. That will be aj minus ai plus 1, right? Aj minus ai plus 1. Or will it be equal to aj minus ai? So this dp relation seems to be fine. I'm not really sure. Let me say that, okay, I have to, okay, first let me actually put this 0 and this n in the array b. Okay, so as to pad it. Okay, if I pad it, then I will have to say that b dot pushback. Let me actually make it a comment. B dot pushback a is the length of that. Then I will say reverse b, and I will b dot pushback 0. Then I will again reverse it so as to bring it to the correct position. Okay, cool. This seems to be fine. And now if I have padded it, now I have to create a DP table. I have to create DP table of this length, right? The new length is what we say the new b dot size. So I will create a DP table of n cross n, vector of n, dp of n plus 1, comma vector of n, dp of n plus 1. One thing is that it is not given to us that what is the value of this m going to be. So I hope an order of n square solution passes, order of n square solution in time as well as in space, but I don't really know. Okay, so this will be the dp matrix that I will create. What will be the base case for this? The very first case will be of length 3, right? All the length 3 cases I have to handle, because that is where I can make a cut. Okay, so I can say for int length equals to 3, and the maximum length will be n, right? 1, 2, 3, 4, right? So n will be, in this case, n will be 5, so it will be less than n. For int length equals to 3, length less than n, plus length. That will be the base case. Then I will have to put an I. Okay, then what will be I for int I equals to 0? I mean, like, what the start position should be. I plus length should be less than n plus I. J is equal to I plus length, right? Or will it be I plus length minus 1? It will be I plus length minus 1, right? I plus length minus 1 should be less than n, because for index 0, length 3 and set 2. Index 2, okay. So some people want the problem link. This is the problem link. Okay, now I know J. Then I have to have another loop. So it will be an order of n cube time complexity then. For int k equals to I plus 1, k less than j. I mean, like, that is where I will split at plus k. Initially, I will set the value of dpij to be int max. I set the value of dpij to be int max. But I have to finally return what we say the sequence. But I'm firstly trying to see if if the algorithm that I'm coding up has the correct answer. Then I will be able to create the parent array to that. dpij will be equal to min of dpij, comma, array j minus array I. That will be the length of the code. That will be the cost that will be added, plus dp of I to k plus dp of k to j. That is a sub problem that should be there. And then finally I will return dp of 0 to n minus 1. That should be correct, but that is not returning the original answer, right? So let me first see if this is returning the correct cost. then we will try to, what we say, create the answer thing, right? Okay, so suppose let us take care of this test case only. For example, 6 and 1 to 5. Let us try to see what it returns there. Is it A? It is B? Bj minus Bi, and then there should go returning 0. Why? I say dpij is equal to int max and length is equal to 3. dpi will be 0, yes. So I plus length minus 1 should be less than n, so that is fine. Is bj minus bi min of dpij, which is initially int max, comma bj minus bi plus dpik plus dpkj. Okay, so I should be returning the correct answer, right? Let me try to see what dpij is coming for each index. Just if I suppose do that, what is this? I j and then I say dpij. I just first want to clarify if my algorithm is correct. I'm just trying to see it. So then it will give me, yeah. So from 0 to 2, the cost is coming to be 2, which is correct, because that is the only thing. I never do 0, 1, 2, 3, 4, right? I never do 0. So this array will change to, what they say, this array will change to 0, 1, 2, 5, 6, right? So the answer will be at 0 to 4, but I'm never computing 0 to 4 here as such. Okay. I'm computing 1 to 4, but I'm not computing 0 to 4. I plus length minus 1 should be less than equal to n, right? N is 4. N is 5 here, so this thing is coming out to be correct. My length should be less than or equal to n. My length starts from 3 and my length should be equal to n, right? Length is less than equal to n, then it will be computed, I think. So that is the thing that, yes. So the answer is 12 and the 12 was minimum. That thing we also knew, right? So at least we are getting the correct TP answer. I mean, like correct numerical value. The issue now comes, how will we, how will we create the lexicographically smallest permutation? Okay. One thing that is not probably given is that is the array of B1 to BM sorted? It is not given, right? It is not given that B1 to BM is sorted. So we have to sort that. Sort of B dot begin to B dot end. Okay, great. So that thing we already know. And now we also know that we are able to come to the correct answer. Okay, so now the problem remains as to how we will create the lexicographically smallest permutation. Okay, so to that, suppose I'm also storing that what was the index that gave me the minimum value. Suppose what was the index that gave me the minimum value? Suppose that I also had this. Rather than doing this, I would have told that if command x is less than dpij, okay, that means dpij is first equal to this, uh, this, and then I can also say that this will be min index. Then I can say that min index of I to j will be nothing but k. Okay. So once I have this, I know that dpij is going to return to the correct solution. So now I have to just probably process that array, process this matrix backward. That in which order will I make the cut? So I can say that vector of int answer initially will be empty. Okay. Currently my endpoint is 0. Int start 0 and n is equal to my end will be n minus 1, right? So till when should I find the sequence of cuts? I should keep cutting on. Okay, then I know that there are two problems in which that I have to find. Okay, the dpij and dpkj. Right. So first, the very first cut will be actually what we say answer dot pushback min int start comma end. But then there will be sub cuts, right? Then there will be multiple other cuts that will also be there. So how should I compute that? Because otherwise I will have to do that recursively, right? I first compute that, then I compute that. Or can I do a recursive function to do that? Probably if I do a recursive function, then it will automatically handle it, right? So let me say that suppose my void recurs to what we say start comma end, and this is the vector of end at answer. Okay, when do I know that this is done? I know this when if start minus end is less than 3, right? If end minus start is less than 3, less than 2. If end minus start plus 1, that is the length, is less than or equal to 2. That means I don't have any answer. That means I don't have to put anything. So in that case, I can return. Else, I will say answer dot pushback min end of ij, min end of start end, and then I will recurse for start to min end of this with this answer, and I will also need to pass my min end, right? And min end, okay. Similarly, then I can recurse from this plus 1 to, sorry, this only to end, and I will need to pass it answer and min end. Okay, and here I will have to have this min end. Okay. I will actually need to have the B of that particular base, not min end, but okay, let us say that I have this. Then I will say recurse of 0 to n minus 1 to answer to min end. But now I will have to change everything in the answer to reverse of that. So then I will have to change everything in the answer to reverse of to basically what was the value in this B. So I will have to say for auto iterative index in answer, index will be equal to P of index, and I can return answer. This should probably work because I'm calculating it in the correct sequence. It should be correct probably. What am I missing? I don't have a semicolon here. Anything else? Probably no. So I'm returning 2, 1, 5, which is absolutely correct. I hope I'm not missing any other test case, but let us test it. Yes, and let us try to submit it. I hope the time complexity passes because we are not given the constraints. Yeah, so we are told that we are failing for the partially correct. Okay, so we have some wrong answer for larger test cases. Why? Okay, so probably the time limit is exceeding, right? Because there is no other reason why it should fail. The time limit can be exceeded because this is order of n cube. Can we bring this to order of n square? When I am computing this dpij, I need to know this thing is always going to be fixed. So I need to know the minimum value of dpik plus dpkj, right? So if somehow I know from I to k, which is the minimum k that stores that, but that I can't do. Currently, I'm at an order of n cube solution, and probably because I'm failing this, I have to get it to order of n square or anything else. No, probably the answer is there some modular arithmetic issue? Yes, there can be modular arithmetic issue, right? Because n can be up to 10 to the power 9. Then if n is up to 10 to the power 9 and all these numbers are 10 to the power 9, 10 to the power 9 minus 1, 10 to the power 9 minus 2, in that case I will overflow, right? Yes. In that case I will overflow. So then I think I will need to have this vector as a vector of long end, uh, long end, and then probably this should work. Because there doesn't seem to be any other issue then. If I'm failing for the large test cases and I know that there is overflow possible, then probably that is a thing. And then this dpij will also have to be something larger than integer max, right? Or not? Eventually it should not, but it can be. So I have to let me make it. I have taken it as a long 10 to the power 17. Then let me first test for the normal cases. If I'm doing some compilation issues, I think I will be doing this matrix. Yeah, because min index is k, but bj minus bi can be larger, right? So yeah, this seems to be fine. Okay, so this seems to be fine, and then let us try to submit it if that is the real issue, because that is what seems to me as to be the issue. And yes, let's try to do it. Correct, that was the issue, and we fixed it. Okay. Great. So basically, how I identified that that was the issue, that was an interesting thing. That here I saw that the value of n can be up to 10 to the power 9. So when we were calculating the cost of the last three indexes, they can be 10 to the power 9, 10 to the power 9 minus 1, 10 to the power 9 minus 2, which will be equal to 3 into 10 to the power 9 minus 3, which is greater than integer max. So there was a chance of an overflow and we fixed it up. Okay, great.
Hello everyone, in this video we're going to talk about the problems from Code Drift Day 1 and the topics are DP and Griddy. So let's get started. The first problem is turn on the bulbs. Now let's give it a read. There are A bulbs lined in a row numbered 1 to A, which are off initially. In one step, you can choose any bulb and turn it on. If you turn a particular bulb on, the bulb 2 places to the right and 2 places to the left of this bulb would also turn on. Bulbs that are already on will not be affected. Formally, if you turn on the bulb numbered x, it will also turn on the bulb numbered x minus 2 if it exists and bulb number x plus 2 if it exists. Okay. Find the minimum number of steps required to turn on all the bulbs. And the problem constraints on A are A can vary from 1 to 10 raised to power 9. Now with all this information, let's move on to solve some examples first. Now let us talk about these two examples. We are given A as 2. So we are given 2 bulbs, right? In case of 2 bulbs, let's say I turned on this bulb. Then I can turn on a bulb which is at position, let's say this is at position 1, then I can turn a bulb which is at position 1 minus 2, or that is minus 1. But negative 1 is not a valid index in this case, right? Similarly, I can turn on a bulb which is at position 3, 1 plus 2, 3. Again, we don't have any bulb at third index, so I can just turn on this bulb. Then after that, I need to turn on another bulb which is at second position. So for A equal to 2, our answer will be 2. Now let us talk about A equal to 4. We'll have 4 bulbs and we can solve it in this way. We can turn on this bulb and we can turn on this bulb in one operation, and we can turn on this bulb and we can turn on this bulb in one operation. So we'll have 2 operations here as well. So for A equal to 4, we need to return 2 as well. Okay. Now let us move on to see the solution to this problem. Now in order to solve this problem, we need to make some observations. Let's say we have certain amount of bulbs here. If I try to turn on this bulb, then I will also turn on this bulb and this bulb, right? Similarly, if I try to turn this bulb on, then I can turn this bulb on and this bulb on, right? So here we can clearly see that if we have 6 bulbs, we need exactly 2 operations to turn all of them on, right? So we can make batch of 6 bulbs and we can turn them on using 2 operations. Okay, so our solution will be, let's say we are given some A, then we'll try to make batches of 6. Okay, we'll try to make batches of 6 and we'll try to turn them on in 2 operations. After that, we'll have some remaining bulbs. So what can be the number of remaining bulbs? Remaining bulbs can be 0, can be 1, can be 2, can be 3, can be 4, can be 5, right? So these are all the values. We cannot have 6 remaining bulbs. Why? Because we can again make a batch of 6. Okay, so these are all the possible values we can have after we have made all the batches of 6. Now let's try to solve these examples on pen and paper. Now we can solve the problem for these values quite easily. So let's do that now. Let's say what will happen if our A is 0. Then if we don't have any bulb remaining, then we have 0 here. If we have one bulb, then obviously I need one operation. If I have two bulbs, I have already discussed this, then again I'll need two operations here. So I'll have 2 here. If I have 3 bulbs, let's say these are our 3 bulbs, then I'll again need 2 operations here. Why so? Because if I'll turn this bulb on, then I need to turn this one as well. Then I need one more operation to turn this middle bulb on, right? So I'll need 2 operations here as well. In case of 4, let's talk about 4 now. 1, 2, 3, 4. I'll turn this bulb on and this bulb on. I'll turn this bulb on and this bulb on. So I'll need 2 operations here as well. Similarly, let us talk about 5 now. For 5, I'll have 5 bulbs. 1, 2, 3, 4, 5. And let's say I turn this bulb on, then I need to turn this one and this one. And after that, I need one more operation to turn these 2 bulbs on, right? So again, in case of 5, I need 2 operations. So here we can see that now I have list of all the values I need to return in case of 0, 1, 2, 3, 4, 5. Now that we have all the values that we need, now let us try to write a formula for this. So let's say we are given some A, then first I need to create all the batches of 6. Okay, so how many batches of 6 I can create out of A elements? So that will be A by 6 and this will be an integer division, right? For all these batches of 6, I can make 2 operations per batch. So I can multiply this with 2. Okay, after that I'll have some of the elements left, right? So in order to know the rest of the elements, I can just do A modulo 6. Okay, and the value of A modulo 6 can vary from 0 to 5 and we can take those values from this table. Either we can store all these values in an array or we can make one observation. For 0 it is 0, for 1 it is 1, and apart from that for any other value which is greater than 1 it is just 2, right? So what we can do here, we can return minimum of A mod 6 comma 2. Why so? Because if A mod 6 is 0, we need to return 0. If A mod 6 is 1, we need to return 1. And otherwise, whatever value we have here, A mod 6 can be 2, 3, 4, 5, then we need to return 2. Okay, so we just do minimum of A mod 6 comma 2. So this formula here is our final answer. Now let's move on to see the pseudocode of this problem. Now let us talk about the pseudocode, which is quite straightforward. Basically, we are creating the batches of 6, then we are multiplying it by 2 because a batch of 6 needs 2 operations. Then after that, we are returning minimum of A mod 6 comma 2. The second problem is yet another string operation problem. The problem description states that you are given 2 strings A and B of same length. In one operation, you can set some AX equal to BX. This will cost you 1 coin. Otherwise, you can also reverse a substring A from I to J at most once. Okay, so you can choose to reverse some substring of a given string and you can do this operation at most one. Okay, so you can either do it or not do it, and this will cost us C coins. Now we need to find minimum operation required to make both string equal. Okay, the problem constraints are length of A and B are equal and they can vary from 1 to 1000. A and B consist of lowercase alphabets only, and cost C can vary from 0 to length of A. Now let us move on to see some examples. Let us talk about these examples now. We need to convert this string to this string. So A, B, C, E, D, A to B, D, E, C, B, O. Here we can see that if I reverse this much of string, I'll just get this string. Okay, so I'm going to reverse it, and the cost of reversing a string is 1. Okay, so I'll add 1 to the answer and I'll just reverse it. Now it will look like D, E, C, B. Okay, so now the characters which remain unmatched are A and A. We need to convert this A to B, which will take again one operation, and we need to convert this A to O, which will again take one operation. For this example, our answer will be 3. Now if I talk about second example, I have two strings here again, and we can see that only the first character is different in both strings, so I just need one operation here. Okay, so in this case our answer is 1. Okay, now let us move on to see the solution to this problem. So basically we can see here that we need to convert this string to this string, right? The solution here is based on dynamic programming, so we can define states here. The states we can have are L, R, rotate. Here L will be the starting point of the string, R will be the ending point of the string, and rotate can take two values, 0 or 1. It will be 0 if we have not used the rotate operation right now, and it will be 1 if we have already used the rotate operation. Now currently my L will be here and my R will be here. Then what I can do, and let's say the index are 1, 2, 3, 4, 5, 6. Then my recursion will look like go from 1 to 6. I need to solve from 1 to 6, and currently our string is not rotated. Okay, so from this string I can come to this state, go 2 to 6 and not rotated. And how can I transition to this state? What I can do, I can check whether this character matches with our first character of string B, and if they match, then I'll add 0 to the answer, otherwise I'll add 1 to the answer. Okay, and then I'll recur for this relation. Apart from this, I can also check the last character of our current string with the last character of our string B, and if they are equal, then I'll add 0 to the answer, otherwise I'll add 1 to the answer, and I can recur for 1 comma 6 minus 1, that is 5 comma 0. Okay, we haven't rotated it. Now there's one more operation that I can do, that is I can reverse the whole string. In that case it will cost me C units, so I'll add C to the answer, plus I'll recur for the same string from 1 to 6, but this time it is in rotated form. So in the similar fashion, I can transition from one position to another position. Let's say I want to transition from this position, then I'll go to 2 plus 1 3 comma 6 comma 0, and I can also go to 2 comma 6 minus 1 5 comma 0. Okay, and apart from that, since it is 0, we can rotate it, right? If it is 1, then I'll cover that case, but if it's 0, I can just try to rotate it here, 2 comma 6 comma 1, and then after that we can rotate it, we can add C here, right? So that's how we can transition. But there is one special case, and that is what will happen after we have rotated the string. Okay, so let's cover that now. Let's say I'm using my rotate operation, then I'll add C to the answer, and I'll transition from 1 6 to 1 6 only, but this time I've rotated my string. Okay, now from this state, as we know that our string is rotated now, that means the substring from 1 to 6 is rotated. Okay, so whatever we have at first position, it should be in the last position in case of second string or string B. Similarly, whatever we have in the last position will be in the first position of string B, right? So from this place, our transition will be, if our first character is not equal to the last character, we'll add 1, and similarly if our last character of string A is not equal to the first character of string B, I'll again add plus 1, and then I'll transition to 1 plus 1 2, 6 minus 1 5 comma 1. Okay, so that is the only transition that I can make, and if I try to write it properly, it will look like this: AL, if AL is not equal to BR, plus if AL is not equal to BR, this condition will be 1, and that will add 1 to the answer. Similarly, if AR is not equal to BL, or that is the last character of string A is not equal to the first character of string B, then again add 1 to the answer, plus go 2 comma 5 comma 1, right? So that's how we can solve this problem. Now that we have covered all the cases, let's try to generalize it. Now let's say our recursion looks like this: go from L to R, and this is root. Then we have two cases here. If ROT it's equal to 1, then we can perform only one transition, and that is we can return go from L plus 1 to R minus 1 with rotation intact, plus we'll try to compare the first character of our current string with the last character of our string that we need to convert it into. Similarly, we'll compare the last character of our first string with first character of the string B, right? So that's how we are going to solve it if we have already rotated the string. Otherwise, we'll have three cases. We can do go L plus 1 to R with 0, plus we'll compare the first character with the first character of string B, right? And I can do the same for last character as well. So what I'll do there, R minus 1 comma 0 plus I'll compare the last character of our string A with last character of our string B. And apart from these two, I can always reverse my string. So in that case, I'll just do go L to R, but this time I'll pass 1 here because I have already reversed my string. Okay, in this case I need to add C. So I can return the minimum of these three. We can return this. Apart from these things, we need to handle some base cases, like what will happen if L is greater than R or if L equal to R. And in this fashion we can solve this problem quite easily. After this, all we need to do is memorize the solution, and that will pass the time limits. Now let us talk about the pseudocode to this problem. So basically we are given two strings A and B and an integer C. Then I have this go function here which has three parameters L, R and rotated. So rotated here signifies whether we have reversed the string or not. And then LR signifies the same thing. L represents the first character, R represents the last character of the current substring we are watching. Okay. If L is greater than R, then it is an invalid interval. We need to return 0. Otherwise, if L equal to R, then we are going to return whether the current character of string A is equal to current character of B. If they are equal, then we need to return 0. Otherwise, we need to return 1. Okay. So this condition, just do that. After that, we have discussed this part here. If rotated is true, we can do just one transition, and that is we'll check the first character of our string with the last character of string B, and the last character of our string with the first character of string B, and then after that I'll do the transition to L plus 1 and R minus 1 with 1, right? Otherwise, I'll have three conditions. I can go to L plus 1, or I can go to R minus 1, or I can go to LR but with rotation as 1. Okay, you can see that here rotation is 0. That means that currently we haven't reversed our string, but here we are trying to reverse it, and since we are trying to reverse it, we are adding C to the answer. Okay, so after that I'm just returning the minimized answer that I'm getting out of all these conditions, and at this part we are basically memorizing the solution. We are just trying to store this solution in this DP state, right? And at the end I'm calling this function go, and it is returning me the optimal answer. So that's how we are solving this problem quite easily. So that's pretty much it for this video. Please like the video if you enjoyed the content. Do subscribe. Thank you for watching. Hey guys, in this video we're going to talk about the problems of code drift day 2, and the topics are DP and greedy. So let's get started. Let's talk about the first problem, maximum XOR with minimum x. The problem description is, given an integer a, select two integers x comma y such that x and y can vary from 1 to a such that they have maximum possible XOR. If there are multiple x comma y's, choose one with the smallest x. So basically we need to maximize the XOR of any two values, and those two values should be in range 1 to a. The problem constraints are a can vary from 1 to 2 into 10 raised to power 9. Okay. Now let's talk about some examples. Now let us talk about the solution. Let's say we are given any integer a, and the number of bits in this integer is x. Then I claim the maximum XOR that we can get is 2 raised to power x minus 1. Or basically, this also means all ones x times. This is binary representation. Now, why do I claim so? Okay, so in order to understand this, let's see how actually the binary pattern works. I'm going to write some numbers in binary here: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 9, and so on, right? So in this binary representation, you can see that number of bits here is 1, here it is 1, but here number of bits is 2, right? Now here we can see an increment in the number of bits, right? Similarly, if we look at this place, we have 1 1, then we have 1 0 0. Again we have increment of 1 in the number of bits, and similarly at this place I can see an increment of number of bits, right? Because here it is 3 and here it is 4. Now whenever we see an increment in the number of bits, we can see that the lowest number with x bits, we can XOR it with the highest number of x minus 1 bits, and we'll get a number with all x bits set, right? So whenever I'll have a number of x bits, I know that I'll always have some number, like in this case a number with x minus 1 bits, which will fulfill our condition of XORing and maximizing the answer to this value. Similarly, here I can see that I have a number with x bits. Okay, we have 1 0 0. Then I am sure that my range from 1 to this number will also include 1 1. Okay, so I can always make 1 1 1 out of it. That's why I said, given a number a who has number of bits equal to x, I can make this number. Okay, and that number is 2 raised to power x minus 1. Moving further, let us assume that 2 raised to power x minus 1 is k. Then we need to create k, right? So what we can do, our answer will be k minus a comma a. Why so? Because we know that all the bits in k are set. So we have something like this. Okay, we have some structure which has all the bits as 1, and if I subtract a from it, and let's say we have something like this, then one thing that we can notice here is wherever we have 1 in our a, I'll get a 0 there, right? So this one is k and this one is a, and if I tend to subtract them, if I try to calculate this value here, so wherever I have 1 in a, I'll have 0 in my answer. Okay, and apart from that I'll just have 1, right? Now this value is k minus a, and if I XOR it with a, which is 1 1 0 0 1 1, right? So if I XOR it back with a, I'll get my answer as all ones. So that's why we can choose k minus a comma a as our answer. But there are two base cases that we need to handle. The first one is, if a equal to 1, we have just one possible choice, and that is 1 comma 1, and the XOR of these two values is 0, which is the maximum we can get. And apart from this, we have one more condition. Let's say our a is equal to k, then in that case k minus a will be 0, right? So we don't want that. Why? Because the range that we can operate in is from 1 to a, so we cannot use 0. So in that case, what I can do, I have one extra information here is that a also consists of all ones now. Why? Because k will also consist of all ones, and since a is equal to k, a will also consist of all ones. So in this case, what I can do, I'll just subtract it with 1. So if I'll subtract a with 1, I'll get 0 at last position, right? Now if I try to XOR this value with 1, I'll get my answer, right? I'll get my answer back as k. So in case of a equal to k, I'll return 1 comma a minus 1. So that will be my answer for this case. Now let us quickly see the code to this problem. We are given an integer a. If a equal to 1, we are returning 1 comma 1. That is one corner case. Otherwise, this x, it will contain the number of bits in our current number, or basically in a, right? After that we are calculating k is 2 raised to power x minus 1, and then we are checking if k equal to a, we are returning 1 comma a minus 1. Otherwise we are returning k minus a comma a. So yeah, that's it. Now let us talk about the second problem. Valid parentheses again. So Robin bought a sequence consisting of these characters. A sequence is valid if it follows any one of the following rule. an empty sequence is valid. If x is valid sequence, then opening bracket plus x plus closing bracket of same kind, or similarly for all, similarly here as well, is also valid. If x and y are valid, then x plus y is also valid. Fine. His brother played with the sequence and misplaced some of the characters. Those misplaced characters are denoted by question mark in string A. In order to make the sequence valid again, he decided to replace the character question mark. The task is to determine number of valid sequences that can be created by replacing question mark. Since the answer could be large, output answer modulo 10 raised to power 9 plus 7. The problem constraints are A can vary from 2 to 150 and length of string A is always even. Now let us move on to see some examples of this problem. Now let's say we are given this string and we need to count the number of valid sequences we can make out of this string, right? So I think we can do this like this. This is a valid sequence. Similarly, I can just change this outer bracket to something else. Let's take the big brackets. And similarly, I can change the outer braces to curly braces. Okay. So this also works. So apart from these three strings, we cannot have any other string. Why? Because we need an opening bracket for this one and we need a closing bracket for this one. And we cannot have the opening and closing bracket for these guys here. Because if I'll have an opening bracket here for this one, then I'll have one element left in between. Similarly here I'll have one element left in between. And we cannot pair up that element, right? So that's why we can have just three kind of strings here. So in this case our answer will be 3, right? So that's how we need to solve this problem. Now let us move on to see the solution of this problem. Now let's say we are again given the same string and this time we need to create an algorithm to solve this problem. So let's start with brute force. So what I'm thinking to do here is I'll say that this is my left pointer and this is my right pointer, and I'll assume that my left pointer is an opening bracket. Okay, then after that I'll iterate on this string from L plus 1 to R, and I'll try to brute force each and every position for the closing bracket of my current position L. Okay, so in this manner eventually I'll reach at some base case, and if that is a valid sequence, then I'm gonna add 1 to the answer, right? So that's how I'm thinking to solve it. So let's try to solve it recursively. Okay, so let's say this is currently our string. Then what are the choices we can make? So for this guy as an opening bracket, I can have this guy as closing bracket. Yes, and since both of them are question marks, if this question mark is this, we can have this here. This question mark is this, we can have this here. This question mark is this, we can have this here. So this question mark can take 3 values. Okay, so we can have this as opening and this as closing bracket in 3 ways, right? So in case of a pair of question marks, what we can do, we can just recurse for the rest of the string and we'll just fix this string that these two guys are done here. Okay, so let's say I am recurring for the rest of the string. What is rest of the string? That is this much, question mark, and since these two can take 3 values, so whatever I'll get answer from this recursion, I'll just multiply it by 3. Okay, because I can do that 3 times, right? Now again let's try to say that this is my ending bracket. Okay, now in this case our ending bracket is not a question mark, it is a curly bracket, right? So that defines our starting bracket as well. Okay, so our starting bracket cannot be any other bracket but a curly brace. So in this case I'm not gonna multiply with 3 like I did here, because in this case I have just one possibility, right? So if I assume that this is my opening bracket and this is my closing bracket, then I need to solve the sub problem of this string and this string. Then I need to solve question mark. So these two strings, I need to solve these two strings separately, right? And similarly, let's say Now I take this as my closing bracket. But in this case, I can see that this is already not a question mark and it is an opening bracket. So it cannot be a closing bracket. So I cannot choose this position. So I'll just move on. So I'll move on to this position. So again, it's a question mark. So I can choose it, and I can choose it in three ways because we have a pair of question marks here. So I'll choose it in three ways. I can multiply it by 3, but I'll get the answer from here. Now, what are the strings that I need to solve independently here? It is question mark, curly, and parenthesis, and one question mark. So these are the strings that I need to solve independently, right? Let's move on to this value. Now for this value, again we have a question mark. So we can see that we'll have 3 choices. And what are the strings that I need to solve it for? We have just one string, that is question mark, closing curly brace, opening parenthesis, and a question mark. So that is my sub problem here, right? Now here you can see that this is a string of length 1, so it cannot make a pair. So this is a base case. So we can conclude here that this string is not going to get converted to a valid string. Okay, so we can return from here. Here we have a string of length 1, so we cannot create a pair out of a string of length 1. It must be even at each and every position, right? So again, I cannot do it here as well. Now I have only two choices left, this one and this one. Okay, and both of them consist of just one string of even length. Okay, so let me remove the choices which are not valid. Now we have these two choices, right? So again we can do the same. So let's iterate on this string. I'll fix my first character of this string. Okay, and I'll assume that this is an opening bracket. But in this case, as we can see that this is not an opening bracket, so this choice is again invalid. Okay, so since it is a closing bracket and we cannot find a pair of this bracket, so we can just return 0 from here, and 3 multiply 0 will be 0. Okay, so this is again invalid. Now let us move on to the second sub problem we have. So here let's fix this character as the first character of our current substring, or the character which will possess opening brackets, right? After that, I'll iterate for the closing bracket. So let's say I'm currently here and I assume that this is my closing bracket. Then in this case, since the closing bracket is not a question mark, I can only do this in one way. So if I choose this as my closing bracket, the sub problem that I'm gonna get is parenthesis and question mark, right? Because these two are selected. Now let's say I choose this as my closing bracket. Now since it is an opening bracket, I cannot do that, right? Because it will be an invalid choice. So I cannot choose this. Now let's try to choose this as my closing bracket. Now again, here we have two question marks. So I can put three kind of values there, right? So my sub problem will have some strings. In this case, I'll have just one string, and that is this one. And we can get the answer in three ways. Now after this, we can see that this pair is invalid, right? Because it starts with a closing bracket. So we can again return 0 from this position. So we'll return 0 from here. So 3 into 0 is 0. Now we have one substring left here. Okay, so for this substring, I'll choose this as my starting bracket. Okay, opening bracket. Then I have this choice as my closing bracket, and since this closing bracket is a question mark, but here our opening bracket is not a question mark, right? It's a fixed bracket. So my closing bracket can be made by just one choice. So what I'll do here, I'll multiply by 1 and I'll say that this is my closing bracket. So the string that I'm gonna get is an empty string of length 0. So in case we got an empty string, that means that we have already paired up all of our brackets, right? So in this case, I will return 1 from here. I'll say that this is a valid choice. Now 1 multiplied with 1, it is 1. Then this 1 will propagate further to here 1. Now I'll multiply this 1 with this 3. So I'll return 3 from this position. Okay, so I'll get 3 from this string. And rest of the values are returning zeros. So that means the number of valid strings for this string is 3. Okay, so that's how we can solve this problem recursively. So basically we can optimize this recursion using memoization. And now we can move on to see the pseudocode of this problem. That will definitely help us understand the recursion better. Okay, now let us look at the code of this problem. So this is our solve function. We are given the string and then we are passing it to a recursive function go, and here 0 is L and n minus 1 is R. Okay, so we are solving it. So now let's look at the go function here. This is L, this is R, right? Now if I is greater than j, we are returning 1. So when I is greater than j, then we are encountering an empty string, right? So as we have already discussed, in case of empty string, we are technically claiming that we have already paired up each and every bracket, right? So we can return 1. And if I equal to j, then currently we have one character left. And since we have one character left, we cannot pair it up. We need at least 2 characters to make a pair. So in that case, I'll return 0. Otherwise, I have this answer variable and I'm memoizing it using this dp table. After that, I'm checking if our vi is not an opening bracket or a question mark, I'll return 0. Because if my string starts with a closing bracket, I cannot pair up with an opening bracket, right? So in that case, we'll return 0. Otherwise, we'll iterate from I plus 1 till j. And for each element, if vi equal to question mark and vid is equal to question mark, so here vi is the opening bracket and vid is the element we are trying to consider as our closing bracket right now. Okay, if both of these are question mark, then we can solve the sub problem in 3 ways, right? That's why I'm multiplying by 3 here. And then I am recurring from I plus 1 till id minus 1 and id plus 1 till j. So let's say this is the string question mark dot 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 question mark dot dot dot. Then this is our first character I and this is our sub character id, which I have considered as our closing bracket. If I consider this as a pair, then I need to recur for I plus 1 and id minus 1, that is this string, and id plus 1 till j, and that is this string. So I need to recur for these two strings, right? So that's why I'm recurring for these two strings and I'm multiplying the number of ways in which we can solve these two subproblems, right? After that, I'm multiplying it by 3 because we can solve our current subproblem in 3 ways because we have 2 question marks, right? Now if we don't have a question mark, we'll have a closing bracket which we can use. So in case of a closing bracket, we can recur for I plus 1 and id minus 1 and id plus 1 and j, and we won't get 3 ways here because I know our closing bracket is something, okay, some character. So our opening bracket should be that same character only. That's why we are not multiplying by 3 here, right? If my vi is equal to question mark, then we have covered the cases. And if my vi is some opening bracket, in that case, I need to check again, right? So here, our vid or our closing bracket can either be a question mark or it can be a reverse of our current bracket, right? Since we know that our vi is not a question mark, that means our vi is some character. So here's the reverse function that actually returns us the reverse of current bracket. Okay, for this the reverse is this, for this the reverse is this, for this the reverse is this. Otherwise it will return an invalid sign. So that means if this is the case, then I am recurring from I plus 1 to id minus 1 and id plus 1 to j, and I am adding that up to the answer. After that, I am returning my answer. So that's how we can solve this problem. So that's pretty much it for this video. Please like, share and subscribe. Thank you for watching.